All right. Okay, so we are now recording. All right, and so let's talk about oscillations first. So oscillations is the final, and I'm hoping everybody has watched my chapter 10 video by now, because I mean it's kind of prerequisite to going to the lab. But to kind of sum things up, as I've said a few times in this class, things or objects move three possible ways. I mean, we're studying mechanics, talking about the motion of objects. Objects move three possible ways. That is translation, rotation, and oscillation. Okay, so translation really is, you can think of a body, as moving as if all of its mass is located at the center of mass. I've discussed center of mass a couple lectures ago as well. That's so, and bodies really do move this way. Things do move in accordance to translational motion as if the entire mass is centered at the center of mass. So this is very much reality. But this is not considering any kind of a close-up extended view of the mass. So this is really like the subjects of chapters 1 through 7. All right, and then rotation, we talk about the second way objects move. That is, we have to now consider the object as being more of an extended mass, an extended body, and that parts of the body, the body is moving around or maybe there's a system of bodies that are moving around at a common axis of rotation or an axis. And so bodies move differently in accordance with how far away they are from the axis. They all move. Maybe in our assumption, they all move at the same angular velocity, but they'll be moving at different linear velocity because they're a different distance away from the axis. So that's the subject of chapters. This is what we did on Tuesday. Subject of chapters 8 and 9. Tonight, we're going to go into chapter 10, which is oscillation. And we're also going to discuss waves. And as I've said before, waves do not actually belong in any of the theories. They are ubiquitous. They are actually across all theories. Waves are actually a state of being. If we go to physics 2, we go to quantum theory, we find out that all objects in the universe are both waves and particles. All objects live in a duality, a dual space. There's a wave-particle duality. So we think of waves as a disturbance that propagates. I mean, as I said in my lecture on waves. However, waves really are an actual essence of reality. So that's a topic for chapters 16 and 17. Okay, so we pop all the way to the end of the book. So we have one more mechanics chapter after this, and that's chapter 11. That's actually going to be on fluid mechanics. In chapter 11, when we get done with chapter 10, you'll say, okay, now we have completed all of solid mechanics. But remember, there are three basic states of matter: solid, liquid, and gas. What about the mechanics for the liquids and the gases? The liquids and the gases will be together called fluids. Well, that's the subject of chapter 11. When chapter 11 is done, we're done with mechanics. Chapters 12 through 15 are thermal physics. 16 and 17 are waves. So we have to cover waves now because of the way the labs are structured. In the labs, there are no thermal labs. So basically, you'll have chapter 10 tonight with a taste of chapter 16, or it's chapter 16, 17. And then next Tuesday, we'll have our final lab of the semester, and that'll be entirely chapter 16 and 17, and that's it. Like I say, there's no thermal labs. Okay, so that's what we're talking about tonight. So let's kind of talk about the theory a little bit before we go into the lab. And then again, like I say, next Thursday, so next Tuesday is the last lab, and next Thursday is exam 2. All right, now, so what are we discussing here? Well, in reality, what we've talked about with translation, bodies move as if all the mass is located at the center of mass. Okay, so we got that down. With rotation, we now consider an extended body. Rotating about some axis. So I might say that I have some body rotating about an axis, and I might say, well, let's go along a radial. Let's imagine I have a point 1 and a point 2. Even though point 1 and point 2 are going to be rotating about, point 2 is going to be consistently to the right of point 1. Now, if I'm standing here at point 1 and I'm on a merry-go-round or something, and my friend of mine is on point 2, my friend is going to be constantly to my right and always about the same distance away from me. So even though we're both moving together about some axis, we are in a same relative location with respect to each other. Now, and again, so far, all I've talked about are rigid bodies. I talk about bodies that do not deform, that have no elasticity. They are solid. They are purely rigid with no elasticity at all. Now, with this chapter, I want to now relax that and consider bodies that can deform, bodies that have elasticity. All right. And so with oscillation, we want to consider bodies that have elasticity. So consider bodies that possess elasticity. That means that if I take some sort of a body, it doesn't have to be circular, it's just any old body, and it doesn't have to be rotating or anything. The body could be moving about, whatever, and I may have, let's say, along some line, maybe this is my center of mass, doesn't really matter so much, but along some line, maybe here's 1 and here's 2, but now 1 and 2 may move with respect to each other. And so sometimes, and it could be two-dimensional, it could be more of a complicated motion, but now they're no longer rigid. They now parts of the body. So parts of the body now move with respect to each other. So I have relaxed rigidity. And so how might a physicist want to model something like this? Well, physicists are going to simplify it and think of each of these little tiny, each little mass element will be a point mass, and they'll be connected by springs. So a physicist might want to take a look at this arrangement or this body or this situation, and then try to make a model out of it. So a physicist might say, okay, well, I got a complicated body, but I'm going to break it up into little mass elements. I'm going to say I have mass M1, mass M2, mass M3, M4, M5, let's say M6, M7, M8, maybe M9, and each one of these is going to have a spring. I'll put the dots first and I'll label them afterwards. So 1, 2, 3, 4, 5, 6. And as well, imagine that each of these bodies is connected by springs. So they can kind of, so the bodies can move with respect to one another. All right, so I may have M1, M2, M3, M4, M5, M6, M7, M8, M9, and let's say these ones, they all have like some sort of a K. Maybe we can just imagine all the K's being the same, or they can be different. It doesn't really matter. All these are math. All these have spring constants, and they all move with respect to each other. I'm not going to write all the K's out, right? So that's how I look at it. Well, why don't I start off by considering the simplest possible case first? Obviously, that's the case. That's where I want to go. But you have to start crawling before you walk, before you run, right? And so what we're going to do is we're going to start off with the simplest case of just one mass on one spring, right? And so if I look at this, I think I have one mass on one spring, and I have a wall here and say a floor. And I'm going to imagine that I can have the mass initially at some equilibrium condition. So here's my mass, and here's my spring. Spring is given by some sort of a spring constant K. The mass is given by M. And right now it's relaxed. Okay, it doesn't want to go anywhere. It's in its equilibrium position. It's totally happy. It is relaxed. We'll say that location, we'll call it X naught. Okay, it's location. We'll say this is the X-axis. Now, let's imagine that we're going to now compress it or stretch it. It doesn't really matter. So we're going to now, I'll just say this. So I'm going to now redraw this picture and say, well, this is where the mass is at equilibrium. That's where that's at its happy point equilibrium. Now I'm going to compress it. Now I mean, well, let's see. What's probably the best thing for me to do? I'll stretch it. Let me stretch it out. I'm going to stretch it out here. All right, and so here's my mass now, my real location, and the spring is now stretched out. And here's where it used to be. And so I've displaced it by some amount, and I'll say that this is the maximum displacement. I'll call this capital X, maximum displacement. Okay, so right now, we remember that if I were to look at an energy argument, I'd say, well, in an energy argument, what do I expect to have happen? Well, I expect this situation to be, potential energy initial plus kinetic energy initial. What's it going to be? Well, initially given that this Hooke's law spring force is a conservative force, it has a corresponding potential energy. What is that potential energy? Well, it'll be 1/2 K cap X squared. Again, that's the displacement. You'll understand why I'm using capital X in a minute. Kinetic energy, well, initially I'm holding it. So kinetic energy is going to be 0, right? Just do an energy argument. And then what happens? Well, we'll call this location 1. I'll call it PE1 and KE1. Well, what's the system want to do? Well, the system wants to return to its equilibrium location. So I let it go, and potential energy will change into kinetic energy. And when you get to the location where the equilibrium is, great. All the potential energy has been converted to kinetic energy, and it's at its equilibrium position. However, bad news. It happens to be going at the maximum kinetic energy at that point, so it's going to be at the maximum velocity. So yeah, it may be at equilibrium, but it's going to blow right through it, so it's not going to stop. So if I call this location, I'll call this location 0, equilibrium. Well, then what's going to happen now is PE sub O plus kinetic energy sub O. What's that going to be? Well, the potential energy now is 0. It's at the 0 potential energy, and it's going to have entirely all kinetic energy, whatever that happens to be, 1/2 mv max, if you will, squared. And what's it going to do now? Well, now it's going to compress, and it's going to go all the way out to negative cap X. So it's going to be full compression. This is full stretch. This is equilibrium position. And then we're going to go full compression. What's going to happen now? Well, potential energy, I'll call this then 2. Potential energy 2 plus kinetic energy 2 will equal what? Well, potential energy 2, now it's all entirely wound up. It'll be 1/2 K negative cap x squared. So again, given I'm squaring it, it doesn't really matter, plus 0. So it's going to have the same total. This is full compression. And this is saying, oh, we have all this, you know, it's going to come to a momentary stop. It's going to unfurl, go back toward equilibrium. All the potential energy will go back to kinetic energy. And of course, it'll have maximum kinetic energy. It'll blow right through equilibrium, go to full stretch again. I have now done one cycle, full stretch, through equilibrium, full compression, through equilibrium, back to full stretch. It's a whole cycle. And the whole thing's going to go over and over and over again. We're making assumptions here. No friction of any kind. No surface friction, no friction. So that means that I predict that just from energy arguments alone, that this system is going to go back and forth forever. Back and forth, just like this forever. No energy will be dissipated. Okay, it's basically going to go in what is called simple harmonic motion. This nice, simple back and forth motion is called simple harmonic motion. Okay, so I've given you this argument with pure energy considerations. The big question is, well, can I do it with Newton's second law? All right, so fine, we can do this with energy. That's great. What about Newton's second law? We really want to do mechanics. Can I do that? Well, let's see here. So what I'll do with Newton's second law is I'll kind of keep the same lingo. I'm going to imagine I'm being full stretch and have it go back, try to have it go back and forth. So what's going to happen now? Well, I'll see that I'm going to do some of all forces in the x direction. What are the forces in the x direction? Well, the only force that's going to be operating on the mass is going to be Hooke's law, and Hooke's law is a resistive force. So it's going to be given a negative kx. The negative sign is because it's always going to be, it's a force that's always going to be resisting the displacement. Whatever the displacement is, that force is going to go against it. And that is the only force. There's no friction in this problem. Weight is entirely in the y direction. I'm only considering x. I don't really care what's going on in the y direction because there really isn't anything. The normal force is balanced out by the weight. None of that is important to me here. So I'm only going to have one operational equation. So that's it for the forces, and that's going to equal ma. Okay, let's recall here that x is a function of time, and a, the acceleration, is a function of time, right? And so if I take a look at this and say, okay, well, let's rearrange this equation. I have ma plus kx equals 0, or I have a plus k. Let's be specific here. I have a as a function of time plus k over m times x as a function of time equals 0. And I have no other equations. Well, unless I do something, I'm in trouble because I have one equation and two unknowns. And so I'm dead in the water unless I can figure something out. And so, yes, how can I figure something out? Well, I go back to chapter 2. All right, so chapter 2 allows me to figure what's going on. So I have one equation. Let me erase the rest of the stuff. And let's rewrite my equation. So what do I have here? I have a of t plus k over m times x of t. Now, but I got to remind myself, and I'm going to speak calculus lingo for a moment. Again, because you'll see why in a moment, but I'm doing things in a notional way. Going back to chapter 2, what do we remember? Well, we remember the velocity is the time rate of change of the position. Oops, we'll start with delta. But I remember that's not the instantaneous form of the velocity. I have to speak calculus to do things right. So I have to say something like what? I say, well, really the velocity is I have to consider smaller and smaller and smaller intervals of time. I have to do what's called a limit as delta t approaches 0 of delta x over delta t. And that gives me what is called dx dt. I basically replace the x's with d, these deltas with d's. Again, that's calculus. This is called a first time derivative of calculus. This is a first time derivative. Again, if you not have ever calculus so far, don't worry. I'm just delving into calculus briefly to show you why the function looks the way it does. Okay, that's calculus. Now, that's how I would talk about the velocity with respect to the position. However, I want the acceleration, so I got to do this same operation one more time. So the acceleration is the time rate of change of the velocity. But again, for the same reasons, that's not good enough. I have to take the limit. And all calculus is, by the way, some people find it to be intimidating and whatever, but it's only algebra with the concept of limit. That's all calculus is. Algebra with the concept of limit. All right. So again, for people who think that calculus sounds like a scary word, it's no big deal. So limit is delta t approaches 0 of delta v with respect to t, or we refer to that as dv dt. Okay, first time derivative of velocity. But remember here that, well, I know what the velocity is, so I can actually substitute for v. And I can actually write that a as a function of time. Let me just kind of erase this. I can actually write that a as a function of time as a second order slope. So with that substitution, a as a function of time becomes what we call the second time derivative of the position. It's basically the slope of the slope. This is what's called the second time derivative of position. All right, so I understand this is calculus lingo, but don't worry, we'll escape this in a moment. What that now means is I can actually substitute for a of t, putting this thing in there, all right? So what happens when I do that? If I do that, I solve my problem, kind of. So instead of a of t, I can write this new thing. And yay, verily, look at that. I now have one equation and one unknown. Actually, let me be more explicit, so I know that x is a function of time. So great, one equation with one unknown function. The bad news is this is a differential equation. Okay. Can I would say watch my video. I'll give you a full 4 more details about this, but differential equations are hard. It's the highest level math class taught here, or taught at the college. And so in some ways, there are some differential equations that have solutions. There's methods. In some cases, there are no methods. Some cases, you have a famous mathematician's name attached to one because it's hard. In some cases, there still is no solution. Some differential equations have $1 million math prize attached to them. All right, and so the question really comes down to is, well, by hook or by crook, if you can find the solution, I mean, the nature of the game here for differential equations is, can you find the solution? X of t. So if you can, then the existence and uniqueness theorem of differential equations states that the solution is unique if it exists. That means stop looking, you have found it. You may have guessed, and if you got it, you got it. I mean, that's the whole thing. You don't have to look anymore. You got it. All right. So that's the beauty here. You can rest on this theorem that says you don't have to look anymore. There's no other solution in the universe that'll satisfy this equation. So the question comes down to, your book just kind of gives us out of the clear blue, but there's nothing out of the clear blue in physics. Everything is derived via logic and proof. But the thing is, you ask the math department, okay, we got these differential equations. Can we solve it? Is there a solution to it? And they will come back to this, yeah, this is something that we know about. And it would be given as little x as a function of time. Okay, what we're looking for is a constant amplitude times the cosine of omega t. They claim that's the answer. Now, you shouldn't believe them. You should go and plug it in yourself and prove it. Now, the question is, what is omega? Well, t, so anything inside of a cosine function or any trigonometric function must be effectively in radians. So if t is in seconds, that means omega must be in radians per second. Now, unfortunately, once in a while in physics, variables, Greek letters are used multiple times, and this looks a little confusing because we're used to omega as the angular velocity. This is not an angular velocity whatsoever. This is actually called the angular frequency. Do not get it confused. Unfortunately, it has the same units as angular velocity, and it actually has the same Greek letter as angular velocity. So it's a little confusing. It is something totally different. This is called angular frequency. It is in terms of, omega is in terms of radians per second. So again, I know you go back a couple of chapters of chapter 8 and you go, hey, I got omega that's in radians per second. It's called angular velocity. Well, no, that's not what we're talking about here. Here we're in oscillations. This is a wave. This is an oscillatory periodic motion. I shouldn't say a wave. That's not right either. This is called periodic motion, which repeats itself over and over again. A cosine function repeats itself forever. All right. So the question is, well, you tell me this, but I got to prove it. So how do I prove it? Well, I'm going to stick it into the equation. So what I got to do, and I'm going to do a little calculus speak. So those who don't follow, that's okay. I mean, the point is what I want to show you. So I say, okay, I got to get the acceleration again. So I got to find the velocity. The velocity is what? The first derivative of the position. So you find out that you got, the amplitude is a constant. Let's build this up. Anybody who's had calculus 1 would know that the derivative of a cosine is a negative sign. And because of what's called a chain rule, I have to delve into the function. I have a function inside of a function. Cosine's a function, but inside of that is a function called omega t. So I have to take the derivative of that as well. And what happens is the derivative of omega t is just omega. That pops out front. So I have a negative omega at cap x sine of omega t would be the slope of this. In fact, this is the position function time. This actually is an important equation to remember. This is actually the velocity of your mass in a spring as a function of time. Your maximum velocity is omega times the amplitude, for instance. But I'm not where I want to be. I want the acceleration. I got to do this one more time. So the acceleration is a time rate of change of the position. So I got to do the game all over again. And so I come to find out, or time rate of change of velocity, I apologize. I come to find out that I got to take the derivative of sine, which becomes cosine. And by the chain rule, again, another omega pops out. So I now have a negative omega squared times cap x cosine of omega t. That's what I want. All right. In fact, I could also, if I'm really smart, I could realize that this is just x of t. I could actually write this. A of t is, I don't know if I'm still on, well, let's see, tell me if I'm on the video here. A of t actually is a negative omega squared times little x of t. I could write that as well, because cap x cosine is just the original function. So basically the functions are very, very closely related. They're off by a factor of negative omega squared. But the question is, does this work? I realize, A of t, which is what this is negative omega squared times cap x cosine omega t. All right, well, let's put that all together now. We know this, let's plug it in, see if it works. Again, you know, someone tells you something, you gotta prove it. So put it in here. Okay, what do we got? Well, instead of this, we're gonna have negative omega squared cap x cosine of omega t. Great. That's what I'm gonna put in there instead of this first term. The second term, plus k over m, what was x and t again? Oh, that's right, is cap x cosine of omega t equals 0. And look at this, I have cap x on both sides, cosine on both sides. This is a solution provided that omega, I'm going to call this omega naught for reasons I'll explain in a minute, it's the square root of k over m. Okay, this is called the natural frequency. Okay, natural frequency of the oscillator. Okay, this is the basic oscillation theory. Okay, that means that this thing wants to, and so I actually have other ways I can define. So this is the frequency, because this system has a spring constant K and a mass M, because it has certain properties. It will oscillate at a natural frequency, and I show you in the video. There's an example of Tacoma Narrows Bridge, where if you force a frequency near right at the natural frequency, if outside forces cause something to vibrate at the natural frequency in which it likes to vibrate, that's called resonance, and that's really bad. That means the system will shake itself apart, like the Tacoma Narrows Bridge. All right. This is the basic theory here. Okay, so this is what we have to remember. And we're going to go into the pendulum tonight, but the pendulum we're going to find out in a moment is just like the mass in the spring. Now I'm going to go and talk about other definitions. This is basically radian, how many radians per second. All right, but what I really want is, I like to have some way of saying, well, how about if I count oscillations per second? Instead of looking at how many radians happen per second, let me just be able to count how many oscillations. Every time I see the spring go all the way back to the far right, I'll call that 1, 2, 3. So a way I can actually count them. Well, yeah, all you gotta do is divide by 2 pi radians. And that way you're gonna count units. So I have this thing called frequency, regular frequency, where I'm just gonna count the number of cycles. And that's just the number of, I'll call this F naught. That's just the angular frequency divided by 2 pi radians for every single cycle. So I can have a relationship that, now F naught, or F, if you will, is your ordinary frequency. And this is in cycles per second, or what we call Hertz, after the great German physicist Heinrich Hertz. Hertz was actually the first person to show that you can have an electromagnetic wave in the laboratory. So that was a precursor of radios, radar, microwaves, everything. Heinrich Hertz is the reason for all that. He made the very first ever radio, if you will. All right, and then finally, you have the period. How long does a cycle take? We call that the period. That's 1 over the frequency, and that's the period. That is how long a cycle is. Now we're going to be speaking that language tonight with the pendulum. Now the question is, you say, okay, well, that's the mass in the spring. That's not what we're doing tonight. We're doing a pendulum. Yes, that's true. But let's remember these equations, okay? And I'll show you how a pendulum is just like a mass in the spring. All right, so talking about the pendulum now. We're going to talk about, first of all, any questions about what I've said so far? No. Pendulum time. That's what we're going to be doing. So pendulum is just another, we're going to find out is another oscillator. So I said a bunch of stuff about the mass in the spring. That's my go-to oscillator, if you will. But let's do something different. Let's now imagine I have a simple pendulum. So simple pendulum, you can make one by basically taking a little very light string, tying it to, say, a ceiling, and the pendulum initially wants to hang straight down. So there it is. We'll have a pendulum as a bob of mass M. There's a string of length L. We consider the string as massless. That means that the center of mass of the system is the center of the bob. Okay, and it's an idealization. Does the string have mass? Yeah, it does, but we're going to say it's negligible. In our situation, we call it massless. Okay, so this is its equilibrium position. In fact, we can actually do ourselves a favor and define this level here as the zero potential energy. I mean, I can start off by talking about potential energy argument again. Okay, call that the zero potential energy. And what do I want to do now? Well, I'm going to take the string and I'm going to kind of I'm going to put it up a little bit. And instead, this is where it originally was. But now I'm going to put it over here. Okay, I'm going to lift it up a little bit. Now I'm going to lift it up, and it's going to be up by some amount h. All right, and there's going to be some sort of an angle theta. All right, so we can look at this and say, well, what would that angle theta be? Well, we know that this length is still L. This is a right triangle, right? This height is L rate. So I could say something like, well, I know the theta, or I know that, for instance, that cosine theta might be, you know, L minus H over L. For instance, if I want to figure out theta, I can figure it out that way. The string is still, this length of the string is still L. That's my hypotenuse. My cosine is what? Adjacent. What is the adjacent? Well, it's L minus H. It's going to be at a certain height H. What's the hypotenuse? L. So again, I could determine theta by taking the inverse cosine of those lengths. All right. But again, we're doing an energy argument. So we just, all we care about is that, well, you know, initially, I can say that I call this position 1. Say, well, you know, initially, we know the potential energy initial plus kinetic energy initial. What's it equal? Well, it's all potential energy. I'm holding the bob. So it's going to have potential energy, gravitational potential energy. Gravity is yet another conservative force. mgh. The kinetic energy, there is no kinetic energy. Now I'm going to let it go. And when I let it go, it's like the oscillator. It's going to lose potential, lose potential energy. It's going to convert potential energy to kinetic energy. Its maximum kinetic energy will be at equilibrium position where it normally wants to sit. The problem is when it's there, it is at its maximum kinetic energy, so it's going to blow right through. It's going faster than it's ever been, and it's going to blow right through. It's going to all the way to the top, and it's going to go at a height h again. Temporarily stop. Have all potential energy, no kinetic energy. Go right back through. All kinetic energy, no potential energy, and it'll go right back and complete one cycle. So when you're counting cycles of pendulum, it's where it starts all the way over, and you say 1, 2, 3. Every single time you return after a full cycle, you don't do this. You don't go 1, 2, 3. That's not correct. You want to have a full cycle, full to the right, all the way to the left, back to the right. That's 1. That's 2. Okay, so make sure that some students get confused by that, but you want to count full cycles. All right, so let's analyze this. So I can convince you that this will go, if there's no energy loss, this also will go forever. This pendulum will go like this, back and forth, some harmonic motion forever, just like the mass in a spring. Now the question comes down to is, well, can I analyze that with Newton's second law? All right, let's see. So we'll not worry about the energy concept now. Let's talk about Newton's second law. So let's bring it up and let's see where we are here. So we have, number one, we have circular symmetry. So it makes most sense with something of circular symmetry to use polar coordinates. So we have, again, we do ourselves a favor by choosing a coordinate system that's convenient for us. We're just observers. So a convenient polar coordinate system, a convenient coordinate system for us would be a polar coordinate. So we have circular symmetry. So we choose polar coordinates. Okay, we choose polar coordinates. Well, polar coordinates, remember, in any coordinate system, in any orthogonal coordinate system that you choose, whether it be Cartesian, polar, or spherical polar, or cylindrical, at any particular point where a body may be, the coordinates arrive there at right angles to each other. So for instance, the radial is going to go straight out like that to the mass. The tangential, on the other hand, is going to be 90 degrees. Okay, so the tangential will be 90 degrees. That's where the velocity is going to be. The orbital velocity is going to be along the tangential. And they are right angles. This is the radial coordinate. And this coordinate is a tangential coordinate. Okay, the tangential coordinate is the one we're concerned about. If I try to do Newton's second law in the radial, well, the object isn't moving in the radial. The object is only moving in the tangential. So what I want to do is, when I write Newton's second law, when I say the sum of all forces is mass times acceleration, this is a general vector law. It's a vector equation. It is agnostic to any coordinate system. When I choose a coordinate system, that is where I will be specific and write Newton's second law in each of the coordinates that matter. All right. So if I were to say, okay, let's choose X and Y, then I would say sum of all forces in X directions, mass and acceleration in X directions, sum of all forces in Y directions, mass and acceleration in Y directions, blah, blah, blah. However, I'm going to choose R and T, R being radial, T being tangential. Then the radial doesn't give me anything. So remember, a vector equation is always equivalent to one or more scalar equations. So the scalar equation that I want this time for the coordinates at play is the sum of all forces in the tangential direction is mass times acceleration in the tangential direction. That's what I want. All right, so let me kind of write it up here. All right, so this is what I'm trying to solve now. Sum of all forces in a tangential direction is mass times acceleration in a tangential direction. Well, what force is what I have? Well, let's look at this. I have gravity, weight, going straight down. And I have, well, this is an angle theta. And it turns out by similar triangles that this is also angle theta. So in my new coordinates, what I would do is I would have these coordinates form right angles, and the part of the weight that's in the tangential direction is what I'm concerned about. And so if this whole weight is mg, that's the hypotenuse, this part that I care about is mg sine of theta. Again, the opposite of theta. Mg sine of theta is the part that I care about. And it's going to be going in a negative direction. So negative mg sine of theta is m times a tangential. No other force matters. I mean, essentially, I already accounted for weight. Any kind of, say, tension force is along the radial. It doesn't matter because I'm smart and I chose good coordinates. So I would have to, if I chose the Cartesian, I'd have to choose components for the tension. But I chose the polar coordinates, so I wouldn't have to do that. So this is the only game in town. This is my whole equation. All right. So what I have here is m times mass m raised to t is negative mg sine of theta. I don't want to cancel out the m's quite yet, and I'll show you why in a second. Okay. So what I have right now is a big mess. I have a non-linear differential equation. So if differential equations are hard, well, when you make them non-linear, they're even harder. Okay, so what I have right now is a non-linear differential equation. So I certainly don't want to solve this. Okay, this goes beyond, this goes to graduate school. So I don't even want to even think about solving this. what I want to do is I want to do what's called linearizing it. I want to linearize this equation. So what I want to do is I want to look at, I'm going to examine the sine function a little more closely. So if somebody were to tell you or to ask you, like an interview or something, define the sine function for me. Well, if you tell them opposite over hypotenuse, that's incorrect. Opposite over hypotenuse is an application of the sine function. What's in your calculator when you calculate the sine function is actually an infinite series. The sine function is actually the following. If you imagine theta being in radians, the sine function goes as theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, on and on and on for forever. All right, that is your sine function. Basically, it is a function. You take your angle theta in radians, and essentially you do this, and it's alternating, minus, plus, so on and so forth. And the factorial, if I say n factorial, again, this means n factorial. Let me write this up here, probably off the camera by now. So this is if you haven't seen this before, this is one of the fastest growing functions in all of mathematics. I put an exclamation mark after something, it's called n factorial. Like a factory, factorial. How do you calculate that? You take n times n minus 1 times n minus 2 all the way to 2 times 1. That's n factorial. So I want 3 factorial. What's that? 3 factorial. I start with 3 times 2 times 1. It's 6. 4 factorial. 4 times 3 times 2 times 1. Okay, that's going to be 24. It grows very fast. 5 factorial. 5 times 4 times 3 times 2 times 1. It's going to equal 120. So you can see I'm at 5 factorial. If you were to put in something like 50 factorial in your calculator, you'd probably blow it up. It's bigger than 10 to the 99. So factorial grows very, very fast. So these denominators are growing very fast. Now, cosine, similar thing. You want the cosine of theta? That's going to equal 1 plus theta squared over 2 factorial. Actually, I think this is minus. Plus theta to the 4th over 4 factorial minus theta to the 6 over 6 factorial, so on and so forth. Alternating signs. And so again, we're not talking about the cosine here, we're talking about the sine. But just to let you know, that is the official definition of your trig function. So when you calculate you calculate something in your calculator is actually doing this. All right. So, and again, before computers, it used to be very, very hard to do these calculations. So you actually had tables where you look these numbers up because you didn't have computers at your hands. You can just calculate. So let's look at the sine function real quick. So sine of theta goes at theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, so on and so forth. All right. Let's consider small theta. Let me consider small theta. Remember, theta is being done in radians. So small theta. And you'll ask me what does small mean. I'll answer that in a moment. So if you take a small number, just as off the top of your head, let's just say I say theta is 0.1. All right, just for instance, I'm not gonna tell you theta 0.1 is small enough. Don't worry. What if I took theta squared? Well, theta squared, when you're talking about a number that's bigger than 1, like 2, squares get bigger. Squared is 4, cube is 8, right? But for numbers that are smaller than 1, the squares get smaller. So it's 0.01, okay? So it's 100th. If I take theta cubed, it's 0.001, a thousandth, right? So if I talk about something that's small, cubes, fifth powers, everything else are going to be really small. And then you combine that with dividing by factorial, that's even going to make things even smaller. So if I consider angles that are small, these higher order terms become unimportant. I can actually neglect them. I can truncate right here. So if I say that I have small theta, I can say sine of theta. Instead of writing sine of theta, I can just write theta. Like you go to your calculator, put your calculator in radians, take the sine of 0.1, you'll find out that the answer is about 0.1. And so that's called the small angle approximation. I'm going to use it right here. All right, so great. I don't have to deal with sine of theta anymore. So I'm going to take my small angle approximation, and I'm going to say, all right, well, I'm going to now, instead of having sine of theta, I'm just going to put theta. This is going to sine theta. So instead, I'm going to say, MA sub t is now negative mg theta. Now, let's go back to the arc length formula. Remember the arc length formula? The arc length is equal to the radius times the angle subtended. So I'm going to consider, whatever this length is, I'm going to linearize. I'm going to say it's small. So I'm going to say that this will be this arc length. I'll call it S. This distance right here at the end of my sector is going to be the radius, which is L, times the angle subtended. So what I can actually instead write is that theta is now S over L. Instead of writing theta, I can sub for S over L. I'm going to write it in kind of an interesting little way here. Put my L down here. And S. And this is really my inertial force. Force is negative a constant times displacement. Have I seen that before? Yeah, I have, haven't I? Mass in a spring. Mass in a spring was also force is negative constant times displacement. I have a mathematical isomorphism, which means that these are absolutely the same mathematical problem, which means that every single thing that I said about the mass in the spring equally applies to the pendulum. I get it all for free. All right, this is what we call a mathematical isomorphism. All right, so I said a bunch of stuff before. So let's see one that's going to be important for us tonight. Any questions about this so far? All right, so when you see something like this, that's a very nice thing, because what you just got done doing is you saved yourself a whole bunch of work. I've already analyzed this problem. And so what I find out is, well, let's see, what is something that I said before? Well, I said that, what did I say? I said that in the mass in a spring, what did I say of mass in a spring? Mass on spring has particular formulas that are only relative to the mass in a spring. Okay, so what did I say? I said, well, the angular frequency, the frequency in which things like to oscillate, is the square root of k over m. I said that the period is basically 1 over 2 pi, the square root of k over m. And I also said, well, that's the, sorry, not the period, that's the frequency, and the period is 1 over the frequency. That'll be 2 pi square root m over k. Well, let's go to the pendulum now. Frequency, 2 pi square root the mass over k. Well, for the pendulum, what is our k? Well, let's go back to what I just got done saying. I said that we had that the force was negative mg over L times S. This is my K in this problem. Mg over L times S. So I'm going to, again, remember, I can, this is a mathematical isomorphism. What I define as what's the K in my problem, this is absolutely mathematical equivalent. So I can literally stick this in here and figure out what the period of a pendulum is. So my K for my pendulum is mg over L. We'll stick it in here. The period is 2 pi square root of m times mg over L. My m's cancel. It's interesting. The period says the pendulum, the masses don't matter. And so what I actually get for the pendulum, if I kind of erase this, my real estate challenge here, the period of my pendulum, which is going to be important to our study tonight, will be 2 pi what? Well, I'm going to multiply top and bottom by L, so by L over G, so it's going to be 2 pi L divided by G. That is the period of the pendulum, independent of mass. You may not expect that. Doesn't matter how big of a mass is, it's independent. This, on the other hand, is the mass on the spring. It does depend on mass, but the pendulum does not. All right, and so this is going to be a go-to equation in our lab tonight. All right, this is our simple pendulum. Okay, and so I can get the frequency by flipping this upside down. I can get the angular frequency. All of this I can get for the pendulum, but the important equation for the pendulum tonight is 2 pi squared L over G. Okay, so what are we going to do with the pendulum? It's a nice lab. We're going to vary the mass. We're going to vary the amplitude. We're going to vary the length, and we're going to vary gravity, i.e., we're going to go on the moon, on the Earth, and on Jupiter. Okay, that's what we're going to do, and we're going to see these things, and we're going to see that the period does not depend on the mass, and the period also does not depend on the amplitude. All right, the amplitude, so again, as this thing goes back and forth, we realize that the amplitude is going to be capital X. It's not going to depend on that. Okay, so that's the go-to equation tonight. That's all I really want to talk about for the pendulum. I mean, again, this kind of quickie version. Please do watch my chapter 10 video. The other part of the lab tonight is waves. Now, waves, we're going to have an intro to waves. All right, and so now it's a little confusing. Now the labs tend to put these labs tend to start putting the oscillations and the waves together. The waves and the oscillations kind of speak the same language to some extent, but you have to remember they're very different. An oscillation is, if I were to look at, for instance, the mass on the spring, and I would want to map it out. Okay, how would it map out? Well, at first, it's going the spring is going to be all the way stretched at a cap X. It's going to come through 0. It's going to go to full compression, negative cap X. Come back through 0, go to full stretch, positive cap X. So what's it going to do in time? Well, in time, this is my time axis. It'll start off at time equals 0 at full amplitude, capital X. All right, here is negative full amplitude. Again, this is a capital letter. Fully stretched. It's going to go through 0, equilibrium. It's going to go to full compression, back to 0, back to full stretch, back to zero, back to full compression, on and on and on forever. And we're going to find out that, well, what does that look like? Well, that's x is a function of t, is the amplitude, cosine of omega naught t. I mean, that's what that looks like. All right, looks like a wave. It's not a wave. It's an oscillation. This is an oscillation. It is periodic motion, which means it repeats itself. But again, it is not a wave. Okay, and we have very similar language. We have frequency, period, things like that, right? But again, what is this mapping? This is mapping a one dimension. This is one dimension. This is amplitude, or basically distance, displacement from the equilibrium, either one direction or the other, and time. This is time. This is a t. Okay, look, it's a cosine wave. Yeah, sure. What about waves, real waves? Well, in this case, there's going to be a lot of similar language, which is a little bit confusing. But in a wave, essentially you solve, a wave is a disturbance that propagates. Now, as I've said, and I said this in a video, and I'll definitely say this in physics too, a wave is actually a state of existence. It's more than just a wave, that it's a disturbance that propagates. But for now, that's what we'll say. We're not in quantum theory yet. So we have two types of waves. We have transverse waves, and we have longitudinal waves. In a transverse wave, the disturbance and propagation direction are perpendicular. What's an example of this? Wave on a string. Electromagnetic wave. Okay, when I say this, I'm going to draw a picture that looks really similar. I'll draw the pull up this longitudinal for a moment. I'm going to draw a picture that's very similar to what I drew before, except different. Okay, so what's a wave going to look like? Well, my disturbance, let's say a wave in a string. I'm disturbing it, let's say, in the y direction, yet that pulse gets propagated, let's say, in the x direction. So now I'm not x versus time, I'm y versus x. Time is now what we call as a parametric variable. You don't actually see it because x and y are both varying by it. Time is these are both dependent on time. You don't see time. Time is a third dimension. All right, and so what do you see? Well, you might see something that looks like this. Looks, very similar, sinusoidal, but this actually is what you see. This is not just a representation of a distance versus time. This is actually what you see in space. This is something you actually look at and see. And so you have an amplitude, we'll say capital X, or I guess in this case, we'll say capital Y, big Y. Maybe down here, negative big Y. Distance from the top to the bottom, from crest to trough, is 2 cap Y. Now, one of the things you can look at and say, well, I want to characterize this wave. So I've characterized this wave, and essentially what am I seeing? I'm seeing something that's going to propagate in space. And I'm going to see the same thing coming past me over and over again. If I'm just watching, I'm sitting here let's say I'm watching for a wave to go past some point in space. There's a crest. Okay, it's going to go down, down, down. Oh, there's a trough, and then back to a crest. And back to a crest again, and back to a trough, back to a crest. And I'm going to constantly be seeing waves going past me. And what I want to figure out is, well, what distance is it along X, where how far in X does the wave go before it repeats itself? Well, if I'm saying, okay, I'm going to go crest to crest. I just saw a crest. How far does the wave travel in X before I see the next crest? Or, you know, and that distance, the distance that a wave covers in a given cycle, it's called its wavelength. So the wavelength would be the distance from crest to crest, or if you so choose, you might pick another spot in the wave that repeats itself all the time. I mean, all points repeat itself. You might decide that I prefer to go trough to trough. That's fine. I mean, if it's a perfectly sinusoidal wave, I can pick any point in the wave and then figure out how far the wave goes until that same point comes, you know, I see that same point again. This is called a wavelength. This is the Greek letter lambda. It's a Greek little l. And again, we keep using Greek letters, all right? Now, if I want to ask, well, how long does it take? How long does it take the wave to do this? Well, you know, to go one cycle, that's called the period. So the period is, let's kind of write these out here. This is our wave language. Lambda, this is a Greek little l. We call this lambda. Okay, that is the wavelength. Typically, we would have that in terms of meters. The time, this is called the period. Again, we're using the same language. This is the time it takes a wave, I would say, to travel a wavelength. In the propagation direction. Again, we're reusing a lot of words, but they actually mean something different. Okay, so we can go back to our basic equation then. Oh, okay, distance and time, huh? Well, I know that what? Distance is velocity times time, right? That's from first day of physics. So what I can actually say is, well, let me rewrite this, is that velocity is distance over time. So wavelength divided by the period is a propagation velocity. But more generally, we know that the ordinary frequency is little f, is given by 1 over t. Again, this is the ordinary frequency. So when I talk about propagation, deja vu, but it means something different. It's something for waves. And again, this is in hertz. And the universal equation for all waves is this one. V equals F lambda. That's the one you'll see over and over again. So waves are what? Well, I can have waves in a string. We call that the speed of wave propagation along the string. I can have waves, I can have electromagnetic waves. Well, that would be the speed of light. When I study sound waves would be the speed of sound. So again, this is the speed of propagation. So if I were to do the mechanics, let's say for a wave on a string, I'm not going to do that here, it's way beyond the scope of this class, but if I were to do that, I'd have to solve a differential equation called the wave equation. The wave equation is actually a partial differential equation. That means that it's one class above differential equations. Okay, it's multivariable. But I would solve a partial differential equation, one of the famous ones called the wave equation. And the solutions are y as a function of x and time. Okay, it's multivariable now. It's going to be some amplitude times the sine of kx minus omega t. You might actually have what's called a phase factor. In general, you might even have a phase factor. Ours, for most of this lab, is going to be 0. But so what's k? K is called a wave number. It's 2 pi divided by the wavelength. Called a wave number. It is in terms of radians per meter. We already know omega. That's 2 pi divided by the period. That is the angular frequency. Radians per second. Phi is a phase. To watch my video, I'll talk about waves in phase and out of phase. Out of phase waves do what is called destructive interference. In phase waves perform what is called constructive interference. We're not going to talk about phase here, but in general, when you analyze a wave, this is the general form of a wave. And so in your lab tonight, you will be asked toward the latter part of the lab, you'll be asked, bottom, there's a table around the bottom of page 5. They want the equation. What's the equation for a wave? This is the equation for a wave. I mean, your equation really would look like this. You don't worry about the phi. That's your equation. Okay, so we're going to talk about that. So I'm not going to talk any more about waves than this. This is what you need for the lab. Please watch my video. But again, we'll have more on waves next Tuesday when we talk about our final lab. But again, I did a little more theory than probably we need to. But I want to make sure that when you guys do this stuff, you know what it is that you're doing. All right, and so in the first part of the lab, we're going to talk about the pendulum. And with the pendulum, your going equation for the pendulum is going to begin. So let's kind of remind ourselves here for a moment. 1 second here, one more time. Make sure I covered everything here. Okay. So tonight, actually, I think that's it. So the main equations, to kind of sum everything up, the main equation we want to look at for this lab will be, we got the first part's the pendulum. Okay, we understand how this all came about. The pendulum looks like what? Looks like 2 pi, the square root of L over G. Okay, so that should be all your period depends on. Okay, L is the length of the pendulum. You're considering a simple pendulum. G is gravitational acceleration. Independent of mass, independent of amplitude. All right, so we should see independence, independent of mass and amplitude. Nowhere in here do you see that. What do we call small angle again? I never got back to that. Small angle, now I find it interesting that Dr. Edmonds considers it 30 degrees. Usually small angle is less than or equal to 20 degrees in my experience. What happens is you can get bigger than, when you get too big, then your theta cube term starts waking up. And so that approximation of linearity that you got from the small angle approximation, that approximation now goes away. That approximation becomes invalid. And so you start seeing answers that do not correspond to what what our theory said. Because what you've done is you've gone outside the bounds of the derivation. That's why you want to derive your own equations. When you derive your own equations, you get to understand what approximations you made. You get to understand, where things came from, the origins of the physics. If you just grab an equation from somebody, you don't really know where they got that. So you might do something, incorrect, like consider 40 degrees or something, that you'd be way off, right? So anyway, we're going to go up to 30 degrees tonight, and I guess to not too bad of an approximation, I guess. But and then the going equation for the waves, the other part of the lab. I mean, the going equation there is that y as a function of x in time, and y is your up and down direction. Oh, by the way, longitudinal waves are where the propagation direction and the disturbances are parallel, like sound waves. Okay, so we're going to primarily talk about transverse waves. Okay, so anyway, we'll talk more about that, and that's all in the video. So again, it's the amplitude sine k x minus omega. That's the going. Those are the two going equations tonight. All right, and so again, one from the theory of waves, one from theory of oscillations. All right, so that's where we are. I'm not going to talk anymore about theory. Let's kind of look at the lab. All right. Any questions right now? I'm going to fire up the first lab. So you go to the lab right up. I'll share my screen. I think I have both of them up right now. Or maybe I don't have either up.
Professor?
Yes.
The only lab due this week is the momentum lab, right?
The only lab due this week is the momentum lab, yes.
And
we are doing 2 labs this week though, but the only lab actually due this week is momentum, yes.
And then the 2 labs that we're doing this week are due next week, right?
Indeed, next Friday. Yep.
Okay, thanks.
Yep, indeed. All right, so I'm going to share my screen. I have preloaded the pendulum lab. And here we go. Just to kind of save us some time, since it seems like it takes forever to do these. Oh, okay. Hang on. Guess I already fired them up. Hang on. Oh, I guess I didn't. Okay, here we go. All right, pendulum lab, here we go. So you should see the first screen for the pendulum lab. And so what you want to do is you want to select intro, just like the lab tells you to do. So I'll do some of this with you guys. Again, I want you to do some of this yourself. All right, so what you have is a pendulum hanging straight down. All right, and the idea is this lab is pretty straightforward in that you just want to change the various parameters and see what you see, see what there is. So part 1, you're going to essentially consider, well, let's kind of look at things first. So let me try to get this Zoom stuff out of the way. All right, so you guys don't see any of this. You just see the lab. I got all these real estate issues. All right, so on the right, you have the ability to change the length of the pendulum. So for instance, right now it's set at 0.7. I can make it shorter, or I can make it longer. Again, I'm gonna initially keep it at 0.7. The mass, I can change the mass of the pendulum with this slider bar, and I can change where I am I have different options. Right now I'm going to stay on Earth, but I can go to the moon, Jupiter. There's a thing called Planet X, but we're basically going to do moon, Jupiter, and Earth. We're mainly going to be on the Earth. And I can pick, you know, friction. Not really going to do any of that. We're not going to consider friction in this lab. And essentially what I'm going to do is I'm going to fill out this table. Now, if you go to page 3 and going into page 4 is a data table. All right. Part 1, you're going to keep the length the same. You're going to vary the mass. You're going to keep the third column is gravity, or the next column over gravity, and keep that the same. And you're going to keep the amplitude the same as well. And then what you'll do is you're going to figure out how long it takes 10 oscillations to occur. So what you'll do is you'll select on the bottom right, you'll select what is called a stopwatch. So the stopwatch will pop out and I'm fighting with this. I'm fighting with Zoom here. All right, trying to get everything away from Zoom. So the stopwatch gives you essentially gives you a timer. Now I'm gonna do the first one. So honestly, in the first, so part 2 of the table. Part 2 of the table, what we're gonna do at that point is, okay, so part 1, we're varying the mass. In part 2, we're going to vary the amplitude. We're going to vary how far, the initial angle which we start. And see, and again, as I said earlier, with our equation, we expect to not depend on mass. We also expect not to depend on amplitude. So if I vary the amplitude, it shouldn't matter. Part 3, the only thing we're going to vary is gravity. So we're going to go Earth, or we're going to go Moon, Earth, and Jupiter. And then part 4, what we're going to vary at that point is the length of the pendulum. So we're going to vary different things and see what happens. So it's going to be a fairly, once you get things going, it'll be a lab where you want to probably have a little coffee to keep yourself going. It'll not be too exciting, but let's see how this works. Okay, so I had to kind of mess with this last night to become good at it. So what I ended up doing is, the first thing I do before I do anything else is I want to make sure, so this button on the far bottom right is your reset button. That resets everything. I want to go with normal speed. That's fine. I want to do that. If I want to stop the pendulum, I get the stop sign. But I just want to do 1, and I want to start off before I do anything. I want to hit the pause button. If I don't hit if I don't hit the pause button, what happens? So let's say I'm going to go 15 degrees, and oops, whoops. Oh, now it's going. All right. I don't want that to happen. All right. And so I'm gonna stop it. And let's see here. Is there some setting I didn't do? Intro window, stopwatch. Okay. Yeah. Okay. It looked a little weird there. Okay. So in table 1, what I would do is I would put, for all the lengths, you have run 1, 2, 3, 4, 5, 6. I'd write 0.70 meters for all the lengths, all the way down that column. For the masses, going on column 2, top to bottom, you're going to want to write 0.1, and then 0.4, and then 0.7, 1.0, 1.3, and 1.5. Again, just as Dr. Edmonds dictates. So again, going down the mass column in part 1, the masses from top to bottom should be 0.1, 0.4, 0.7, 1.0, 1.3, and 1.5. G, we're going to be on the Earth. So your entire column for the first, again, we're only doing the first 6 runs right now. We're only talking about part 1. All right, so your length should only be the first 6 of them should be 0.7. All right, we're only doing the first 6 rows. Gravity, I put 9.81 all the way down for the first 6 rows. Again, we're only doing the first 6 rows. We're only doing part 1 right now. Amplitude, what I want to do is before I do anything else, I'm going to hit the reset button. that resets everything. And of course, when I hit the reset button, I have to go retrieve my my stopwatch again. All right, and so the stopwatch, where do I get rid of this? Yeah, I minimized it. Sweet. Okay. Didn't know I could do that. All right, so there's my stopwatch again. And I don't want this system just to start going. I'm gonna have everything kind of in suspense. So before I do anything, I'm gonna hit the pause button. And I'm gonna make sure that this is 0. I'm gonna hit this go button. Okay, and so, and you'll see is that in the stopwatch, you'll see that goes to a little stop square. So again, hit the pause button, hit the go button, so that when I finally do hit the go button, the stopwatch will start simultaneously. And I'm going to set all of these runs. If you watch me displace, my angle is getting bigger and bigger, right? And so I want to pick 15 degrees. I want to pick an angle that I think is a very safe angle. So I'm waiting until it reads 15 degrees. And I'll stop. So I have everything in suspense. My mass is at, so that angle is at 15 degrees. Okay, I want my mass to be, actually I want my mass to be I'm gonna pick my mass to be a ½ kilogram all throughout here. So I'm gonna move my slider. I'm gonna pick my mass to be a ½ kilogram. Okay, I think that's I would say a safe mass for right now. Actually, no. The first mass should be 0.1 kilograms. Never mind. 0.1 kilograms is my first mass, right? So, and then, so the amplitude for those first 6 rows for part 1, I'm going to have all of them be 15. All right. So for part 1, the first 6 rows, the length, I'm going to look at it one more time. The length column should all be 0.70. The mass column should be 0.1. Then 0.4, then 0.7, then 1.0, 1.3, 1.5. The G column should all be 9.81. The amplitude column should all be 15. Okay, now we're going to start filling in some details. So what I'm going to do, and I'm going to be very careful. Remember, the system is starting at the far right. When it goes back to the far right, I'm going to start counting. That'll be 1 cycle. I'm going to figure out how long it's going to take. I'm going to use my stopwatch, and I'm going to, the best I can. I'm not known for my coordination. The best I can, I'm going to try to stop this thing when it hits the 10th oscillation. So I'm going to hit the play button, and we're going to figure out how long it takes to do 10 oscillations. So I'm going to hit the play button. Okay. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, stop. Okay. When I did it, I mean here it's 17.07, for instance. So 17.07 seconds. And again, I stopped it. I tried to see those little hash marks are there. There's like 2 little hash marks that are set in there that where the string at the endpoints lines up with those hash marks. I try to make sure the strings line up with the hash marks before I click the button. It's a little bit of a coordination thing. When I did it last night, I actually got 17.23. Here in front of you, I got 17.07. So again, that little 07 in the far right is a number that runs between 0 and 99. So that's a decimal. So that value there should be 17.07. Okay, that's the seconds. That's what you put. So I'm in the very first row. Run number 1 in part 1 on page 4. On page 3 in the top row. Now, what I'd write down if I was you would be 17.07. But the next column over, that's the time for 10 oscillations. See, I want to average it out. What I really want is a time for 1 oscillation. So what I want to do is the number that I should write in the very far column would be the number for 10 oscillations divided by 10. Dividing by 10, of course, is easy. All you gotta do is move the decimal. So if I said 17.07, in the column for time for 10 oscillations, well, the time period, i.e. the time for one oscillation, should be 1/10 of that, or it should be 1.707. Just move the decimal to the left one. You're dividing by 10. Why do we do that? It averages things out. You're basically, if you just try to time one oscillation, you might be low or you might be high. Well, it just kind of averages everything out. So dividing by 10 kind of helps to, average out errors, right? And so you time it for 10 oscillations, but then you divide by 10 to get it the time for one oscillation. Okay, so on the very, very first row of the data table, I would read from left to right. It'd be run 1. I'd read length 0.70, mass 0.1, G 9.81, amplitude 15, that's 15 degrees. Time for 10 oscillations, one further to the right, 17.07. Time for one oscillation, 1.707. Okay, any questions about that? Okay, so I'm going to stop this thing and hit the stop sign. Okay, it goes right back to where it was. What I'm going to do is I'm going to actually hit this little little arrow on the bottom left of the stopwatch to zero it out. And what I'm going to do now is the very first thing I'm going to do is I'm going to change the mass. So the next mass I want to consider is 0.4. So I'll move the slider over to 0.4. Okay, so I'll move the slider over to 0.4, and I want to do the experiment again. Keep the length the same, keep the planet the same, keep everything else the same. But before I do anything, I got to make sure I better pause it. So again, I'm going to hit the pause button, and I got one more thing to do. I'm going to hit this little button, this little the little play button on the stopwatch too. Again, that coordinates the stopwatch to start when I hit the play button. So again, you're going to want to hit the pause button on the bottom. You want to hit the go button on the stopwatch. Okay, now I'm going to reset it. I've changed the mass. I'm going to do the exact same thing I did before. I'm going to take it to 15 degrees. Okay, it becomes deja vu after that. There it is, 15 degrees. I'm ready to go. Now I'm going to count out 10 oscillations again. So I'm going to hit the go button. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, there I got 17.09. All right, so 17.09. So that means that's the time for 10 oscillations. So I'm on the second row. I'm on the row that has a mass of 0.4. Well, that's the time for 10 oscillations. And I want the period, which is the time for one oscillation, I divide by 10. So I'd get 1.709. So again, it looks like it's not changing much, does it? I'll do one more with you, and I'm gonna ask you guys to do the next 3 by yourselves. So let's set this up again. All right, so hit the stop button, and I'm gonna hit the little, so again, watch me carefully. I'm gonna hit the clear button, or reset button on the stopwatch. And what's the next mass? So again, one more thing, the second row for part 1 should read length 0.70, mass 0.4, G 9.81, amplitude again 15. The time for 10 oscillations, I think it was 17.09, and your time 1.709. Again, as you're doing this, I'll do one more with you, and then we'll move on to the next one, and I'll let you do the next 3 by yourself. Okay, so again, watch me carefully. What did I do? I reset the stopwatch. I'm gonna go to the next setting. The mass setting. The next setting has got to be 0.7. Take the slider over to 0.7. There you are. That's set. Now I don't want the system starting before I really wanted to, so I'm gonna put it in pause. So again, 2 things: hit the pause button, hit the go button on the stopwatch. Now I'm ready to go. I'm going to set it back to the amplitude of 15. There it is. We'll do the next one together. Now, what am I going to do? I'm going to hit the go button or the play button. And I'm going to put my mouse right on top of the stopwatch so that I'm ready to click the stopwatch when it's ready. So I mean, I develop a little method. So once I hit the go button, that puts everything in order. And then I'll stick my mouse right on top of the stop button so I'm ready to stop the stopwatch as soon as I hit the 10 oscillation, okay? So here we go. All right, and we'll count them off. 1, 2, 3, 4, 5, 6, 7, 8, 9, and hit stop right now. 17.22. I was a little slow that time, or maybe I was right on time. Who knows? 17.22 is what I'd get there. So again, that would be what you stick in for the time for 10 oscillations. In the very far right column, you divide that by 10. That's just moving a decimal point. That'd be 1.722 at that point, right? So again, my third row in part 1 should read 0.7 for the length, 0.7 again for the mass. Now the mass is 0.7. G is 9.81, amplitude 15, time for 10 oscillations, 17.22, and then time for 1 oscillation, that's the period, is 1.722. And I'm going to have you do the next 3 by yourself. You'll find out the next 3 should have very similar time periods. Because why? Because as we saw in our derivation, the period for a pendulum does not depend on the mass. Again, forget what I mean. You're trying to prove that the theory is right with this simulation. So don't let your theory persuade or give you some sort of a prejudice in the experiment. You may find out that your theory is wrong, right? So you got to do the experiment with the attitude that you're trying to disprove the theory. All right. And so again, this is the part where we're just varying the mass. The next part, part 2, as you walk through that, well, part 2 is really at this point, it's going to vary the amplitude. And you should again see that varying the amplitude should not make a difference either. So let's do that part. So I'm going to stop this thing. All right. So I did the first 3 rows on part 1. So again, your 4, 5, and 6 you want to do yourself. Now you already know, you should already have written in there for 4, 5, and 6 on rows 4, 5, and 6 for part 1. You should already have the length written in as 0.7. G, well, actually your mass should be 1.0, 1.3, and 1.5 for rows 4, 5, and 6. Your G should all be 9.81. Your amplitude should all be 15. And then your job is to fill out those squares, those 6 squares to the, or those 6 squares to the right. I'm skipping over now to part 2. Okay, so we're leaving part 1. You're going to do the last 3 rows by yourself. I'm going to do part 2 now. All right. So for part 2, the way I did it is I kept the length at 0.7. So you're going to have 6 rows for part 2. All the lengths from top to bottom, the way I did it all for 0.7. So 0.7 from top to bottom for part 2. I'm going to keep the mass at a constant 0.5. That's what I did. So I stuck the mass, instead of 0.7 or whatever it's reading right now, I just stuck it to 0.5. I felt that was a fairly safe mass. I mean, you can really pick it at whatever you want, but I stuck it to 0.5. You can pick whatever mass. So my mass column reads 0.5 from top to bottom for part 2. My G reads 9.81. I'm staying on Earth. 9.81 all the way down the column, all six rows of that column for the G column for part 2. Now, my amplitude is what we vary. We're going to start the pendulum at, remember the last experiment, I started everything at 15 degrees. Well, here we're going to vary that. So according to what Dr. Edmonds wrote, your first row, your run number 1 should be 5. And then below that, 10, 15, 20, 25, and 30. So that column should read from top to bottom. Instead of all 15s like before, now it's going to be 5, 10, 15, 20, 25, and 30. Okay? Because that's what we're varying now. We're varying the amplitude. All right? So let's see what happens. We should see that it doesn't matter. That's what our theory predicts. All right? Well, let's see what happens now. All right, so I do all that. Let's say I got 0.7 for my length, 0.5 kilograms for the mass. Gravity is still set. Let me clear out my timer. I'm going to pause it like I did before. I'm going to hit the go button on the timer so everything's ready to go. Okay, let's see here. The first amplitude is not 15, but 5. So let's take it over to 5. Okay, so 5 means it's going to go back and forth by just 5 degrees. So a very small approximation. All right, so let's get ready to time. We're going to do 10 oscillations. Ready to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hit the stop button. Okay, I got 17.06 for that one. Again, that's the time for 10 oscillations. And of course, you divide by 10, you just move the decimal point. Your time for 1 oscillation or the period will be 1.706. Okay? So first row of part 2 should read the way I did it. Length is 0.70, mass 0.50, G 9.81, amplitude 5. Your time for 10 oscillations 17.06. Your time for 1 oscillation, i.e. the period, 1.706. Okay, it looks very similar to the previous numbers, doesn't it? Well, it should, because the pendulum motion should not depend on amplitude. But again, we need to prove everything. So stop it, hit the stop sign, ready to go on to the next one. So, what we'll do now is I'll just clear out. So I'm going to hit the pause button. I'm going to hit the reset button on to 0 out the timer. Hit the go button on the timer. So I'm ready to go. I'm in suspense. What's the next amplitude? 10. All right. So I'm going to go now and start it at 10. And now that's a new amplitude, and I'm going to count out 10 oscillations. Remember, oscillations are when it comes back to, it's in the far right now, goes far left. When it comes back to the far right, that's when I'm counting. How many times it hits that far right? That's a full cycle, full oscillation. All right. I'd say full oscillation. Yeah, oscillation. That's right. So here we go. I'm going to hit the go button now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, stop. Okay, 17.05 is my second reading. So that's the time for 10 oscillations. Of course, you divide that by 10, you get 1.705 for the time for 1 oscillation. Okay, well, I'll do one more with you, and then I'll let you do the final 3. I'm gonna stop it. Okay, so what's the deal? Well, it's very similar, deja vu. I'm going to hit the reset button on the timer. Okay, it's zeroed out. And hit the pause button, hit the go button on the timer so it's ready to go. It's a suspense. Everything is staying the same except what? The amplitude. And I'm going to go to 15 degrees now. All right, here we go, 15. 15 degrees, ready to go. And I'm just going to hit the play button and count out 10 oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. 17.02. Okay, so my third row would read, for part 2, it would read 0.70 for the length, 0.50 for the mass, 9.81 for the G, 15 for the amplitude, and then 17.02 for the time for 10 oscillations. Divide by 10, you get 1.702 for the time for 1 oscillation. So you're seeing the pattern here, you know. And so the next 3 trials will be amplitude 20 degrees, then amplitude 25 degrees, amplitude 30 degrees. All right. So you should have all the lengths for those next 3 trials should all be 0.7. All the masses will be 0.5. If you choose those lengths and masses, is up to you. All the G's should be 9.81. And again, I mean, all the lengths should be the same for this part anyway. Whatever you choose, all the masses should be the same, and all the G's should be the same, whatever you choose. I mean, you may choose whatever you want, but they all need to be the same. The only thing that should vary is the lengths, and they should vary as 5, 10, sorry, not the lengths, the amplitudes. They should vary as 5, 10, 15, 20, 25, and 30 degrees. All right. I'll let you do the next 3 by yourself. Now, part 3. We'll just do all 3 part 3. I mean, there's only 3 of them anyway. So part 3, what we're going to vary now is what planet we're on. Okay, we're going to change G. Now we're going to start seeing changes. Remember, the period was T is 2 pi squared L over G. So we start changing G, we should start seeing some differences now. So what I do now is what I'm gonna pick is I'm gonna keep my lengths all at 0.7 like I did before, 0.7 meters. Keep my mass at 0.5 just like I did before. I'm gonna make my amplitudes all start at 15 degrees, but I'm gonna pick different planets. Now, the lab tells you the gravitational acceleration on the moon. So I mean, we can just write these down. Your G column, I'm gonna do the moon, the Earth, and then Jupiter. So your G column from top to bottom for all 3 trials should be 1.63, 9.81, 26.0. Again, 1.63 meters per second squared is the gravitational acceleration on the moon. 9.81 meters per second squared is the gravitational acceleration on Earth. And 26.0 is the huge gravitational acceleration on Jupiter. All right. And so those are the 3 columns. So what are we going to do? Well, again, I'm going to keep everything the same. So I'm going to keep my length at 0.7, my mass at 0.5, but now I'm going to change gravity. And I'm going to do the moon first. So I'm going to select the moon. And now, so the gravity slider bar goes way low. And so, and we know the moon is going to be 1.63. What do I expect to have happen? Well, I know that T is 2 pi square root L over G. So G is in the denominator. I'm putting a smaller value in the denominator, which means I'm making the fraction bigger. I expect the period to really slow down when I do this, okay? Because I'm reducing the denominator. All right, so what I'm gonna do is I'm gonna put everything in suspense now. So hit the pause button, hit the little play button, get ready to go. And I'm gonna pick all my amplitudes to be the same. I'm gonna pick them at 15 degrees. And it doesn't matter, but I want to be the same. Oops, 15, please. All right, 15 degrees. Length of 0.7, mass length of 0.7 meters, mass of 0.5 kilograms. Gravity is way low. It's the moon, and so this should go real slow. All right, so it's going to happen. 10 oscillations. 1, 2, 3, 4. I hit this clock here. 5, 6, 7, 8, 9, 10. You guys are all asleep now. All right. So here we go, 41.72. So if I go in the first row, should be 0.7 meters, 0.5 kilograms. Gravity should be 1.63. I'm going to keep the amplitude at 15. And I got 41.72 seconds. So quite a bit of a larger number for 10 oscillations. And of course, I'm going to do the same game. I'm going to divide that by 10. And so the period, or i.e. the time for one oscillation, should be 4.172. All right. So pendulums go very slow on the moon, as we see. So I'm going to stop, hit the stop sign. I'm going to return back to Earth. Whoa. Stop sign. All right. And I'm going to zero out. I'm going to refresh the time or the stopwatch. I'm going to select the Earth again. So now we're going to do the Earth, and everything else should be the same. Same length, same mass. I'm going to put the pause button again to put it in suspense. Hit the play button on the stopwatch, put that in suspense. And I'm going to put the amplitude back to 15 degrees, get it started. Now we're on the Earth. It'll be faster. Why? Because I'm increasing G, so I'm making the denominator bigger, hence the period will be smaller. So again, we'll count out 10 oscillations, see what happens now. All right, here we go. I think I'm ready to go, yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, stop. 17.10. Again, a number that you've seen before, right? We've been doing everything on the Earth. So again, the second column should then read, and then of course the far right row divided by 10, 1.71. So the second row, I'm sorry, should read for you 0.70 for the length, 0.50 for the mass, 9.81 now for the G back to Earth, 15 for the amplitude. That's what I did. I got 17.10 or 17.10 for the time for 10 oscillations, and of course the time for one oscillation, you divide by 10, 1.71. Okay, that's the second row. Now we're going to go to Jupiter. Hit the stop sign, and I'm going to select Jupiter. That's going to put it all the way practically to the right. All right, I'm going to refresh. What we expect now is that, well, now my denominator, my period is big. So my period's gonna be really fast. So I'm gonna have to wake up and make sure I count 10 oscillations really fast now, right? And so that's what I expect. So I'm gonna put the put it in pause. Again, hit the pause button, hit the go button on the stopwatch, and I'm gonna set the amplitude back to 15 degrees. But I gotta be really quick now with my finger because Jupiter is very fast. It's exactly the opposite of the moon. All right, so let's count off 10 oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, stop. Oops, man, I didn't stop fast enough. Start again. Sorry, I got a little. Let's do that experiment again. I don't know why it didn't respond to me. All right, here we go. Jupiter set. Sorry about that, guys. All right, same old, same old. I'm gonna set it back to 15 again. I guess my fingers aren't fast enough. All right, 15 degrees. Do it again. And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I got 10.91. Sorry, I hit the button again. 10.91 is what I got. All right. So your bottom, so again, the far right column, you divide by 10, 1.091. So my bottom row of row number 3, my Jupiter row for part 3 should read from left to right 0.70 for the length, 0.50 for the mass. G should be 26.0. Amplitude 15, that's now constant. My 10.91 was the time for 10 oscillations, so 1.091 the time for 1 oscillation. So you see the pendulum goes a lot faster on Jupiter than it does on the Earth. And again, so things are working pretty well. And I have part 4. Part 4, now what you change at this point is going to be the length of the pendulum. Now, as we remember, T is 2 pi squared L over G. The pendulum period is proportional to the square root of the length. So that means essentially the longer the pendulum, the longer the period. I.e., the short little pendulum is going to go fast, and the big long pendulum is going to go slow. All right, and so that's what I expect there. So again, I'm on the top of page 4 in the lab. Now I don't know why Dr. Edmonds gave you 7 rows. I would leave the 7th row blank because we're only doing 6 different lengths. So the lengths should read. So the first column is a length column. So the very first column from the trial numbers. I mean, he didn't put a continuation on this table. So the first column, the leftmost column next to the trial numbers, so it'll be the lengths. Those numbers should read from top to bottom: 0.20, 0.40, 0.60, 0.80, 0.90, and 1.0. Again, that first column should read from top to bottom: 0.20, 0.40, 0.60, 0.80, 0.90, and 1.0. The next column, that's what we're varying now, the length. The next column over is the mass column. I'm keeping that at 0.5. So all 6 of your masses should be 0.50. Next column to the right is your gravitational acceleration column, your G column. I'm keeping all that at 9.81. I'm staying on Earth. So I'm keeping that at 9.81, all of them. Next column over is my amplitude column, and I'm keeping all those at 15 degrees. That should read 15. So your leftmost column are the numbers I gave you. The next column to the left is the mass. That's all, for me, it's all 0.50. Next column to the right is the G column. I'm keeping that all at 9.81. Next column to the right is the amplitude column. I'm keeping all those at 15 degrees. And it's going to be same. I'll do the first 3 with you, and then from there, I'll let you do the last 3. Okay? So what am I going to do? Well, I'm going to keep, the length column is what I changed now. So you'll notice the pendulum getting smaller. So right now it's sitting at 0.7, so I'm going to shrink it to 0.2. So the pendulum is little now. I shrunk it. Keeping the mass at 0.5 kilograms. We're going to go to Earth now. I'm still in Jupiter. Oops. So I'm going to go to Earth. So now we're at 9.81 meters per second square on Earth. And I'm going to refresh the stopwatch. And each trial, for me, I'm just going to go at a safe amplitude of 15. Whoops, and I screwed up because I didn't hit the pause button. All right, hit the pause button, hit the go button on the speedometer every single time, or else what just happened will happen to you. All right, now I'll reset it. So 15 degrees, it's stubby, it's just a little harder to control. All right, little pendulum, it's only 0.2 meters long. I'm going to count out 10 oscillations. So again, it's going to go fairly fast because why? Well, again, the period is directly proportional to the square root of L. So that means for the smaller L, the smaller the period. A small period means it's going to go fast. It's not much time between oscillations, or not much time during an oscillation. So let's count out 10 oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. I got 9.23 on that run. All right, so your first row, if you go with my data, your first row of part 4 should read from left to right, 0.20 for the length, 0.50 for the mass, 9.81 for the gravity, 15 for the amplitude, 9.23 for the time for 10 oscillations. You divide that by 10, you get 0.923 for the time for 1 oscillation. That's the smallest period we've seen tonight. So again, time for 10 oscillations is 9.23. The time for 1 oscillation for what this, which is the period for this particular setup, is going to be 0.923. Okay, that's your first data point. I'm going to stop it. I'll refresh my stopwatch. All right, now make the pendulum longer. The next data point Dr. Edmonds wanted you to choose is 0.4. 0.3, 0.4. Notice my pendulum's getting longer now. Longer pendulum. Expect a larger period. Okay, everything else is the same. Mass stays the same. Gravity stays the same. Remember to hit the pause button, hit the go button on the stopwatch, and then I'm going to go back to 15-degree amplitude again. Okay, ready to go. Now I'll count out 10 oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. Okay, I got 13.24 for 10 oscillations. And of course, the period for 1 oscillation divided by 10, you get 1.324 with this data. So for you guys, if you want to stay with this data, second row of part 4 should read from left to right, 0.40 for the length, 0.50 for the mass, 9.81 for gravity, gravitational acceleration, 15 for the amplitude, 13.24 for the time for 10 oscillations. Divide that by 10, you get 1.324 for the time for 1 oscillation. Number's getting bigger than before because the length is big. The length is longer, and of course, the period of the pendulum does depend on the length. The square root of the length, in fact. Okay, I'll do one more trial with you guys. So hit the stop sign. Okay, I'm going to refresh the stopwatch. And what's next? 0.60 length. So I'm going to make the length longer. Put the slider bar, make it 0.6. You notice that the length is getting longer. Okay, and again, mass and gravity all stay the same. I'm going to hit the pause button and the go button on the stopwatch, reset the pendulum to 15 degrees. As before, deja vu, there it is. And I expect, because the period depends on the square root of the length, directly proportional to that, I expect the period to be slower. And I expect that trend to continue as I make this longer and longer. So let's count out 10 oscillations again and see what happens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, hit it. 15.74 is what I get that time. So, and again, the time for 1 oscillation, 1.574. So the third row should read 0.60 for the length, 0.50 for the mass, 9.81 for gravity, 15 for the amplitude, 15.74, you want to keep this data, for the period for the time for 10 oscillations, and of course the time for 1 oscillation, i.e. the period, is 1.574. I'll let you guys do the next 3 on your own. Okay, so I did this whole lab on my own and last night. And again, if you follow all these parts going through page 1, I mean all the way to the bottom of page 2, it's exactly what I did. And I'm just filling out this data table. Now, the next part is graphs. So all of you hopefully have Microsoft Excel. It's probably the easiest thing to do is in Excel is to make these graphs. We want a graph for all 4 of the parts. So you're going to have 1, 2, 3, 4, 5 graphs. You want period versus mass, period versus amplitude, period versus gravity, period versus length, period squared versus length. Now I'm going to kind of do the graphs in front of you to show you what they look like with my data. All right, so bear with me while I fire up Microsoft Excel. I did this last night. I did not do the graphs yet. I mean, I kind of know what they look like. I just left that to do in front of you. I mean, I did it, but I erased my graphs. All right, so here we go. I have this little file called pendulum data. So this is my completed experiment. Whoops. What you're complaining about. All right. So you'll see my Excel here. Actually, I'm gonna stop sharing for a moment. So you'll see the lab go away. I'm firing up Excel right now, so that's what we're waiting for. Then I'll show my Excel. All right, Excel's coming up. Does anybody not have Microsoft Excel? Hoping you all do. So Excel is one of those great skills in life to have. So the better you are at Excel, easier it is to be a technical person. I've been doing Excel since I was a little guy, so I've gotten pretty good at it. All right. I'm going to share my screen. And now you'll see my Excel spreadsheet. And so I've noticed that from previous classes that people are at varying levels of comfort with Excel. Some people are very comfortable, some people are not comfortable at all. So, okay, so you should see a Microsoft Excel spreadsheet, I hope. Okay, what I've done, and please don't just copy my data. I'm just gonna, I'm gonna show you. This is the data I did. So my data is a little different than your data. And so what I did is I mapped out my part 1. Now, what I want to do is now Excel's a little backwards in that your independent variable is actually what you put on your left column. Your dependent variable is what you put on your right column. So this is actually going to be my y-axis. So you kind of read this as an x, y point, if you will. So this was my data from part 1. That was my mass versus period. Here's my data for part 2. And this was my data for part 3. Again, you'll see the data we just got done doing is a little different because on any given day, I'm not going to do the same thing, but it'll be statistically a very similar thing. Part 4, you notice that I have the varying lengths. Here's the various periods, and then you'll look and say, okay, here's part 4 again, the same lengths. But you notice I put a little formula in here instead of. So I put in here. I mean, in the text input field, you see C13 equals C13 times C13. What does that mean? Well, C13 is that particular cell right there, C13. I squared it. I could have put SQR probably if I wanted to, but I just basically took the cell, multiplied by itself. So all of these are T squared. Now, why did I do that? Well, I know that the period goes as a square root. So let me show you something real quick. This is kind of an interesting little trick. So let me go back to my whiteboard briefly. Okay, so why are we doing the T squared business? Oops. Well, we notice that the period goes to square root of the length. So what would I expect to see? I would expect to see something like this. A square root function, if you remember back in your algebra days, looks kind of like, it kind of goes like this, right? It's always increasing, but essentially, square root of of 0 is 0, and then you go square root of 2, so you have 2, but you have 1.4 square root of 2. Square root of 4, it doesn't climb as fast. You know, it's you know, square root of 4 is 2. So you might go all the way up to 81. Square root of 81 is only 9. So it's gonna be a slowly increasing function. What happens though if I consider the following? Instead of the square root function, I do the following. I square both sides. I'm going to square both sides of this equation. T squared. Square the left, I square the right. 4 pi squared L over G. Now, if I decide instead, can I have a cute little trick here? Let's say instead of I'll consider the following. I'll imagine graphing T squared versus L. So my variable that I'm on the graph now is T squared. That's my variable. What I've done now is I've turned this into a linear equation. So what I should see now is the following. I should see a nice straight line because I'm considering T squared as my variable. Now I have a linear equation, and my slope should be what? My slope of this line should be, and this is a y equals mx kind of thing, right? My slope should be 4 pi squared over g. So if you have something that's based on a square root, you can linearize it by just taking the square and imagining that your variable is t squared instead of t. T squared versus L is linear. You should see a linear behavior when you do the t squared. That's why we're doing that. Okay, so when you do t on the first part 4 graph, you should see something that's like a square root. Let me go back and share my my Excel again, and we'll just do this together. I'll show you what buttons to push, how to do this. All right. All right, so there we are again. Now, how do I do this? Well, I'm going to do the part 1 graph. And, you know, so when I first started doing part 1, now some of you guys are more comfortable than others. If you're totally bored with what I'm doing, you know, understand that some in the class is probably not. All right, so again, I'm just going to highlight all of this, all my numbers. I'm going to go and select Insert. Okay, and the insert's going to give me a little different view. And what I like to do is I like to go to the area where I have various types of charts to pick from, and I'm going to pick what we call a scatter plot. So I'm going to pick this guy with all those little dots all over the place. Basically, the first, you know, upper left, you know, option. We call it a scatter plot. Let's see what that looks like. Looks like this. And what you can actually do is, you want to make it nice and big and pretty, you can actually right-click on this. Well, actually, let's do the following. Let's right-click, because one of the things he wants you to do is he says all graphs must have a title and axes labeled. Okay, that means you want to make it look professional. I'm going to right-click, and I'm going to move the chart. I'm going to select Move Chart. Okay, Move Chart basically means I'm going to make a new chart. I'll just call it, I don't know, I'll call it mass. I'll call it M and T. M versus T. You know, for the period, something simple. And what you'll notice is that now you have a brand new tab that's going to form. You have a tab that's M versus T, and then you're going to get these little data points. And then what I'm going to do is, you'll notice that something kind of peculiar here. These data points, they're all over the place, right? What's going on with that? Well, the reason why it looks like this is because you're looking at it way too close up. What you really want to do is you want to expand the view. You want to click on the y-axis, and you want to change you're looking at it like a microscope. You know, it's really a line, but you're looking at it too closely. So what I'm going to do is I'm going to select that y-axis. I'm going to do a right-click on that, and I'm going to go to Format Axis. Okay, and I go to Format Axis. What I'm going to do is I'm going to say, you know, look at this. My minimum is 1.71. My maximum is 1.74. I mean, I'm looking at this with a microscope, right? I'll make my minimum really a 0. And max maybe around 2. And there it is. Now I'm going to look at that. Now if you look, you see that. Now you have the y-axis going from 0 to 2, and you see that in reality, those points are lined up. When they're lined up, that means that's a constant. That means that, you know, and so let's also change another thing. We want axes, right? So I can make the title axis. I can click on that immediately. Actually, you know what? Let's just do a format. I did page layout. I want to pick a different format. I want to pick one that has, I think one that has maybe axes labels. No, I don't want that. Let's pick this one. What about one that has, well, one of them should have an option for axes. Hang on one second. I have a little difficult time even seeing this stuff. All right, let's see. Page layout. I don't want page layout. I want, yeah, here we go. Ah, here we go. No. Give me a second here. I normally know what to do. All right. Let's go back. Oh, I should know it. Yeah. All right. So here's my plot. Give me a second. My brain's not working here. Oh, maybe it's view. Sorry. View. No, that's not it. Very strange. All right. Well, there should be a way to control your axes. All right. Give me a sec. Maybe I should have done that before I. View. Maybe under custom views. No. All right, hang on one second. Let me do this again. I don't know why it's not working. It's probably obvious. I'm gonna get rid of that. So hang on one second. Let me do this again. I'm going to select. Yeah, I'm selecting it. I'm gonna go back to insert. Go back to the scatter plot. All right. I gotta have it. So here you have this. Oh, here we go. So I don't know why this option didn't happen. Notice up here, I have one option. If I go and click a little bit to the left, I have various chart types. No. Should have an option to give myself some axis labels. Well, I don't know why I'm not seeing this. Well, I have a title. I'm trying to get the axis labels. All right, let's see if there's an option here. Format chart area. No, I don't want to do that. there should be a page layout. I'm not seeing something. All right, custom views. All right, well, anyway, the title should be something like mass versus length, maybe a simple pendulum. Now, there should be a way of giving you a y-axis and an x-axis label. I am not, I'm not seeing how to do that at the moment. Format chart area, maybe? No? There should be a way of doing this. I don't know why Excel's not responding to me appropriately. Usually this is an easy thing to do. I've done it a million times. Page layout. Page setup. No. Does anybody know how to get the axes labels? Am I just missing something? Anybody with me? I don't know if there's something that's I'm not seeing. Is anybody here? Hello? Are you guys with me?
I think they're typing in the chat.
Oh, okay. I can't see that. If you're typing in the chat, I can't see that. All right. Normally it's page layout. There's usually an option to get axis labels. I am simply not seeing it.
I believe you have to press that plus sign on the side of your graph and it'll give you options.
Oh, well, there you go. Usually I don't need, oh, axes type. Thank you. How sad is that? Usually there's a selection in the, never mind, that's embarrassing. All right, so axis, axis title. All right, thank you, whoever that was. So let's, for title, I'd say that this is going to be, what is this on the side here? Well, it's going to be the period in seconds. The axis title on the bottom. Well, what are we varying? We're varying the mass. We can maybe say the bob mass, kilograms. And as I said before, we see all these data points. Well, again, we're looking at it through a microscope, so we really want to format the axis. And I'll say the minimum value for the axis, I'll let that be 0. I think the max is set to 2 when I do that. Great. And that shows you that it all lines up. And of course, you can do is you can go right click and you can move the chart. And I'll move the chart to a new chart. And looks like I did it a little too fast, but there it is, new chart. And I might call it M you don't have many characters in this field down here, so I say M versus T. And what you'd do is you'd print that out, you turn it in. Now, what does that constant tell me? That constant says that as I vary the mass, the period doesn't change. It is a constant. That's another way of saying that the period does not depend on the variation of mass. And so you can put a little line in there if you like. So you can go back to your graph and you can say, well, I want to put in a line, or maybe I want to put in a trend line. So I might add a trend line. That gives you a line. Anything you like to do. I mean, you might want to put a line there. So so that would be one thing you can do. All right, so that would be the kind of graph you'd want to turn in for part 1. Okay, part 2. My data for part 2, again, should be deja vu. That's where I vary the amplitude. So again, what I'll do is for those who aren't familiar with Excel, I will select all that field. That's how I'm putting in the part 2 data. That was my data when I did the experiment. I selected the insert tab. I'll just select scatter plot. And again, I'll hit that plus button again and axis titles. Now, what should my chart say? Well, my chart should say period versus amplitude, simple pendulum. Or, if you might want to say something else, but that's what we're doing. That's overall what we're doing. Again, this is very important, for you as scientists to develop, nice graphs, because graphs are how you communicate. So what's on the left-hand side again? Period in seconds. You always want to state where your units are. If you don't put units on your plot, it means nothing. You need to put units. Very important. In this case, what is it? Amplitude. Now, what is it that we're doing? Well, we're essentially varying the period we're varying the period versus the amplitude. The amplitude of your system is going to be in meters. It's going to be how high or low is your oscillation. Remember, you're following. Well, actually, not in meters. I apologize. I'm thinking of the mass of the spring. It's actually in degrees. Your amplitude's in degrees. So it's going to be how big of a swing are you going to get? So 5 degrees, 10 degrees, so on and so forth. So again, this particular situation for part 2, you're going to vary the amplitude. And again, you're looking at it way too close up. You're looking at something that's going from 1.71 to 1.75 seconds. So you need to essentially zoom out. So we'll go back to format axis, and we'll pick, let's say, a max of 2 seconds. Minimum of 0. And I do that, it should maximize out of 2. And notice again, it's a straight line. You can add a trend line if you want, however you like to do it. But again, when I do the period versus the amplitude, that straight line tells me that the period of the oscillation is a constant, does not depend on amplitude. And so I can say, I can print this out directly, or if I want to make my own tab, I can again say move chart, and I can move it to its own tab. And I can call this the T versus, I don't know, A or AMP, if you will, amplitude. I don't have any characters, that's why and you make a new tab. And so it's constant. Your part 3 is going to be where you're on the Earth, or sorry, you're going from the Moon, the Earth, and Jupiter. You're varying gravity. So again, you'll go back to sheet 1. I might just relabel this what I call sheet 1. I might just call it data. I typically do that. It gives you sheet 1 as the default. All right, part 3 is gravity. Select all of that for gravity. Select the insert. And there you go. And you just get 3 data points, nothing much to sneeze at there. Now, for gravity, I expect there to be, you know, there's not a lot to actually plot here for gravity, but let's at least put our chart labels on like we did before. Now, again, the left-hand side, as usual, is going to be, so what did we do here? Yeah, so the periods actually varies quite a bit in this case, so you have to do things a little bit differently. So let's see here, period versus, I don't know, say G or gravitational acceleration if you want. Simple pendulum or G on different celestial bodies. I don't know. Being wordy here. Simple pendulum. It may rap on me. It did. That's all right. You can pick a different way of saying it, but you get what I'm saying. Left hand side is a period, so actually it's already. I don't really have to reset the range like I did before, because it varies quite a bit. It's certainly not constant. And your axis would be G. Actually, yeah. What was my data? Yeah, it goes all the way out to the period goes all the way out to 4.1 for me. And gravity goes all the way out to 20. Let me look at this. Hang on, look at the data again. Oh, I screwed up. I don't know what I did there. Oh, that's right. Hang on. My data is messed up. All right. Give me a second here. I screwed something up. So gravity, period. All right. I think I did a copy paste error there. All right. So gravity. This is all messed up. So my period, I think those numbers are right. All right. My period, 4.159, 1.73, 1.0. That's what I got. Gravity was 1.63. For Earth, 9.81. Jupiter is 26. All right, there you go. That's weird. I had a little copy paste error. All right, insert. Do it again. We'll do the scatter plot. All right, a little different now. Again, I don't have a lot of data, so your data is not going to look too rich. But again, what are we doing again? Period versus G for different celestial bodies, or for different, not just period versus G. As G changes now. Simple pendulum. Good enough. Too wordy otherwise. I think I'm given that. How do you change G? Well, it's inherent because you're changing the gravitational acceleration. You're going to different planets, or you're going to a moon. All right. So axis title. Again, period. You want to make it look professional as possible. That's in seconds. Don't forget your units. And of course, on the bottom here, the horizontal axis is G. And that's in meters per, it's a little hard to, I bet you I can highlight S and make it be a superscript. There you go, meters per second squared. And that's as good as I can get there. And I can make that into, I can do a move chart there. So move chart. And I'll do new chart. And this will simply be T versus G, something like that. And that's just for your own organization. It just names the tab. And there you go. So again, there is a variation between period and G. It really ought to be a 1 over square root variation. But anyway, there's not enough data points to really show that. Okay, now we do the last part, the part 4. So go back to data. Part 4, we're going to do the period versus the length. We have 5 data points for that. Can select insert, select the, and notice that it looks kind of like that square root I told you about. All right, so again, if I had a 0, it would be at 0, and I would just basically be following along this square root. And I could put a line through there, and in this, and if I so chose, but you notice it's definitely not linear. Okay, so this would be period versus length. Simple pendulum. And choose a little plus sign. Axis titles. All right, now for my axis titles, I can pick, period, seconds, and length in meters. What the heck did I do? All right. I did something wrong. All right. Sorry about that. Do that again. I deleted it. All right. Do it again. Sorry about that. Insert. And scatter plot. Oh, it just popped up again. What the heck happened? All right. I really don't know. All right. Axis titles. Let's try to do this right this time. So again, it looks like a square root. Period in seconds versus length in meters. And it would say something like period versus length. So we have one more plot to do. All right, and I might do something like put that as a new chart. So again, it gets a little boring after a while, but some people have seen this a lot and some people have not. So period versus length, simple pendulum. Oops, sorry about that. I forgot I'm doing the chart tab. So we'll just say period versus L. Sorry about that. All right, so there it is. Looks like a square root. And now if we do t squared versus L, we should see that it should become linear. So go back to data. One more. So highlight all of this data. This is period squared. See what it looks like. So again, hit insert, a little faster this time. Hit the scatter plot And notice now it looks linear. I can actually draw a line through that data. So this would be period squared. How you want to say it, period squared versus length, simple pendulum. Maybe I'll make this the two small or superscript. Home font superscript. I highlighted the two, and now it becomes little. I'll go and hit the little plus sign. Axis titles. Again, what am I doing? Different than all the other ones. And then this is going to be period squared. That would be in seconds squared. I'll see if the superscript works for that. It does. I'll make it look professional. And period, I'll highlight this too. All right, so that's pretty much what you want to do. This is a very graph intensive lab, so that's why I'm spending a little time on this. Again, this is a skill to definitely develop. And one more, we'll just stick it as a new chart. So move chart and new chart. And I'll probably say something like, I don't know, T2, and this is just for your convenience, so it doesn't, you don't have to be so pretty about this one. Versus L, this just labels the tab, and there you go. So you would print these off and include these with your lab. All right, so then this is the Excel. I mean, some of you are more familiar with Excel than others, but graphs tell you a lot of information. You know, a graph is worth 1,000 words. So a graph will tell you what the relationship is in a general sense. All right. So I'm done with Excel. I'm going to stop my sharing on that. So stop sharing the Excel. Any questions about the Excel? Okay. The other part of this graph is the waves. Oh, actually, let's see. Post-lab questions. So again, this is now you have the graphs, now you're going to answer questions about them. So from the period versus mass graph, does the period appear to depend on mass? Well, we saw that the period versus mass was constant, so it does not. So you would say from the graph, the period versus mass relationship shows a constant relationship, or shows that the relationship is a constant over versus mass, so it does not depend on the mass. Period versus amplitude graph, again, you would again state from your data that it does not depend on mass. It does not seem to period does not seem to depend on the amplitude. The period versus gravity graph, same kind of thing. Period versus length. You're gonna essentially answer questions based on what you just got done seeing on the graphs. 5, again, I'm on page 4. Number 5, explain how you can graphically determine G of Earth using period squared versus length graph. Obtain the value of G by doing this. So what you can do, actually, is if I look at the period squared, remember I told you the slope was 4 pi squared divided by G? Well, what I could do, let me go back to my whiteboard. If the slope is 4 pi squared over G, well, if I say that the slope is, we'll say the slope, I'll call it S. Well, that means that in my graph, whatever the slope is going to be S. I mean, it's some number that I read off my graph. If I did everything in seconds and meters, it should be meters per second. It should be some sort of a second squared per meter, whatever. So I would say that this is the S for my graph. So S equals 4 pi squared over G, or I can basically switch partners here and say that G is 4 pi squared over the slope. So I can actually use the graph of the period squared versus length and get from the slope value, calculate G. And so let's see if that works for me. Let me go back to my my plot real quick, and I'm trying to answer number 5 on page 4. Go back to my plot, my Excel, and see if I can do this. Probably when I blow it up like I do on the move chart, it seems to be harder for me to see it. But anyway, I'm going to go and share my Excel plot again. Let's see how we can do this in case those who are not familiar with trend lines. Again, we'll be really quick about this. I know I'm going to try to do a little review tonight too. I know that. I apologize. It's like fitting a size 10 foot in a size 8 shoe, you know. All right, so back to the pendulum, share. And I want to do period squared versus length. Okay, so that nice linear plot. It's already there for you. How do I do this? How do I figure this out? Well, what I can do is I'm going to kill this format chart area thing. All right. What I can do is I can basically select any of these points. All right, and they all light up. They're all highlighted. I'm going to right click, and I'm going to say I'm going to go down. And there's going to be an add trend line, all the way almost down to the bottom. So I'm going to click on that, and what I can do is I know that this is going to be linear, so I can select linear. It's already pre-selected for me. All right, and then what I can do is scroll down, and I can select display equation on chart. That's going to give me an equation, okay? And this comes up really dinky. Can't even see it. So I'm going to right click and say select. Oh, goodness. Let me try to select it all. I'm gonna make it bigger. I'm gonna highlight the whole thing. I don't know. Excel sometimes doesn't work very well. All right, so that's a really dinky looking equation. I'm gonna make it large. I'm gonna go to home, and I'm gonna make it's a size 9 font. Come on, guys. I'm gonna make it big. I'm gonna make it like size, I don't know, 28. Does that work? Yeah, I can read that. Good. My old eyes. All right. So what I see is a y equals mx plus b relationship. And of course, the b should be pretty small. I mean, I have some error, so it's not going to be 0. But if I look at that, what do I see? I see y equals, okay, so let's kind of look at this. So I have y equals 4.1414x. Okay, so that's telling me period squared is 4.1414 times length. That's what that tells me in my world. So that means that the slope, so period squared, is 4.1414 length plus some b. Doesn't really matter. So I'm going. I guess it's 0.0441. Let's put that in. That's my y equals mx plus b. 0.0441. Okay, I'm going to go back to my whiteboard in a moment. Okay, so there's my trend line. I got a nice equation out of that. I'm going to stop sharing. And let's go back to the whiteboard. And what does this mean? Well, I have a value. This 4.1414 is my value for S. And so if I look at this and say, okay, well, that's my value for S. That's that slope that I got. I should get some sort of a value for G now. So what should that be? I should get some estimate. It's not going to be 9.81. It's not going to be something pretty, but hopefully it's close to 9. So let's see. What do I get? For my experiment, I use my pendulum, and I want to find G on some planet, in this case, the Earth. So 4 pi squared divided by what? 4.1414. I mean, again, it's kind of crazy, all these decimals of precision, but I'll use it. If I go to my calculator, what do I get? I get 4 pi squared. 4 times pi squared, it gives me 39.478, blah, blah, blah. divide by 4.1414. I get a value G that's 9.53. Well, you know, it's the rough expression. I mean, there's error. The real value is 9.81. And I just did what? I did just 5 measurements, 5 data points. And I linearized the graph. There's some error. You know, I don't have the greatest manual dexterity. So again, I got, for my roughness, I was able to at least get a value G that's fairly close to reality. There's error, 9.53 versus 9.81. Any questions about getting the value G from the linear plot? Okay, you're probably more manually dexterous than I am, so you'll probably get a better value than I got. Again, that's how you get that value. That's number 5 on page 4. All right. Continuing, number 6 on page 4. Explain how you can graphically determine the length of dependent using a period versus 1/G graph. And again, we just did that. You can kind of repeat or kind of go through a little bit of what I just got done doing. Explain how S is your slope, and that your equation is going to be what? It's going to be G is going to be 4 pi squared over S if S is your slope. Okay, waves. Waves are not so bad. I mean, we'll go through that fairly quickly. I don't know what he wraps 2 into 1, but I don't know. So let's see here. All right, I'm going to fire up the waves now. So waves intro.
Hey, I have a quick question.
Yes.
So I'm pretty sure other students are wanting to know this, but I have work in the morning. Is there any way we could do the test review part tomorrow or Saturday? If that way you don't rush through it, or if anything, and that way we get the right material you need to write down, if that's okay with you.
Well, I mean, I don't think I'm going to be much longer.
For the test review?
Test review, I'm not going to do the whole thing, right? I'm just going to do a few problems.
Okay.
I think the waves are the longest. So, I mean, I think just bear with me. I just want to go through the waves really quickly, and then there's not much to it. And then
Okay.
from there, so yeah, then I'm only going to do like 5 problems in test review. So
Okay.
I mean, I don't want this class eats up enough of my time as it is, and this is all pro bono. So
Okay.
that's right now. So anyway, let me just kind of fire up the waves real quick. I mean, I'm kind of going over. It's a little bit deliberate because some people don't know Excel very well, and so this is a very Excel oriented. He wrote this thing for University of Physics students. I'm trying to even the bar. Okay, so let me. I'm firing up waves right now. So sure. Yeah, I'd like to be doing something else too. All right, waves is firing up. When it comes up, I'll put it over on Zoom, and then there's only a couple pages on this. The waves is not as long. All right, and so in fact, we'll just kind of do the waves together real quick because there's not much to it. Okay, so let me share it with Zoom real fast. All right, share screen again. Okay, so when you fire up the waves, you'll have this, this view right here, and it says, okay, well, select water. So we're going to do water waves. So I click that, okay, and you get this. And so the first part of this lab kind of just tells you to get familiar with it. I mean, I'll just kind of show you as we go along, all right? And so the first part of this is this, we want the water, okay, so we want to consider either continuous wave or a pulse. Okay, so we're going to want CW. CW means, he doesn't even really tell you this. I guess he does, yeah. Continuous wave. That means the wave is going to be your regular sine wave. We don't want to do a pulse. We'll do continuous wave. Number 2, I'm on page 5 of the procedure. Number 2 says, set the frequency slider to the middle. Okay, it's already set that way. The frequency slider, this is the frequency of the water drop. So water's going to drop in there and create these waves, okay? You want to use the stopwatch feature. So the stopwatch, you just grab it off of this display here. The stopwatch is right there. So we'll go. It's going to be very similar to the last experiment, but not as lengthy. And so from the period value, we'll calculate the frequency, angular frequency. Again, he doesn't really tell you how to do this. All right, and so let's so I'll kind of show you how I did it. I'm gonna essentially time essentially 10 of these drops and figure out how long. So you're gonna see a table on the bottom of page 5, and so in the table you're gonna have period, frequency, angular frequency, wavelength, wave number, amplitude, and phase velocity. Okay, so we're essentially gonna fill out that waveform. So I'm going to, before I do anything, I'm going to select the pause button again, okay, and I'm going to hit the go button on the stopwatch to kind of put things to suspense. And I want to get things ready. I'm going to hit this little green button that's going to start causing water droplets. So everything's ready to go. And now what I'm going to do is I want to compute how long it takes for 10 water droplets to occur. All right, so here we go. And again, it's going to drop. So we're going to count 10 drops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. Oh, yeah, start this again. Stupid computer didn't do. All right, reset. Sorry. All right, reset. Come on, computer. All right, do this again. Okay, reset this. Pause button. Okay, continuous wave. Go button. I don't know what happened. All right, get in suspense. Okay, start ready to do the drops. All right, hit go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. Okay, I got 16.02 seconds. Again, that's the time for 10 of these waves. Now you divide by 10. So in that little table, the period should be for you 1.602. Okay, 1.602 should be your period. Now your frequency is going to be what? 1 divided by the period. So I would take the frequency 1 divided by 1.602. In this experiment, I put 0.624 for your frequency. Okay, 1.602, 0.624 would be your frequency on this one. Okay, so I had different numbers. So let me write down your numbers real quick. Okay, so yours is 1.602. 0.624. All right. So again, I'm reading the table from left to right. So far, the period I'd have 1.602. That's the time it took for 10 drops. Each drop starts a wave. 1 divided by the period is the frequency in hertz. That's going to be 0.624. Okay, so I'm just developing. Again, the period is in seconds. The frequency is in hertz. It's 1 divided by the period. The angular frequency is 2 pi f. All right, so that 0.624, just multiply by 2, multiply by pi. So I do it, I get 3.92 radians per second. All right, now I'm going to stop this thing. I'm going to stop it at a good point right when a drop happens. Boom. Okay, I'm going to stop this thing, and I'm going to get out my measuring tape. And I'm going to try to measure the next column over is wavelength. Wavelength is done by a measurement. So I'm going to try to pick a spot on the wave. And I'm going to maybe pick one of the fronts of these bright circles. Again, it's going to be a little rough. And I'm going to figure out how far until I get the front of the next circle. Maybe like that. So maybe 2.8 centimeters. but I'll say, I gotta get this in SI, so I'll say 0.028. That would be the value in the fourth column. That's the wavelength column. What's the wave number? 2 pi divided by lambda. This is lambda right here, 0.028. So 2 pi divided by 0.028, wave number 224.4 radians per meters. And so, and then your amplitude, how do you get the amplitude? Well, what you got to do is, what you're looking at is a top view. But if you look on the bottom of this graph, you see side view. Side view shows you what it looks like on the side. And so if I want the amplitude, what I can try to do is try to figure out how tall this wave actually is. It might be a little harder to do, but let's just try to get an idea, a rough estimate about how tall the wave is. I'll try to get it roughly where 0 is. A little bit rough, and to a peak. And so I'm going from the bottom to the top. Well, an amplitude is really going to be going from this 0 to the top. So what I'm actually getting is twice the amplitude when I do this. And I'm getting like 4 centimeters. I'm going from the trough to the crest. That's equivalent to 2 amplitudes, right? Amplitude is really from the center to either the trough or either the crest. So the amplitude is going to be half of that. So I'd say my amplitude should be 0.02 meters. And so the phase velocity is a fancy way of saying how fast is your wave propagating. And so, as we said, V is equal to F lambda. Remember, that's the general equation for all waves. V equals F lambda. That's the phase velocity. So I would multiply F, which is 0.624, multiply by lambda, which is, in this case, 0.028. And I'd have 0.0175, I guess. Or I'll call it 0.017. That's meters per second. That's my phase velocity with all that I've determined. What would my general wave look like? So again, going back, I'm going to stop sharing my screen. What would my general wave look like with what I just got done doing? So again, reading from left to right, on that table, you'd have a period of 1.602 seconds, frequency 0.624 hertz, angular frequency 3.92 radians per second, wavelength 0.028 meters, wave number 224.4 radians per meter, amplitude I got 0.020 meters, and then the phase velocity we just calculated 0.017. And so we're able to now, so I'm going to erase all, this is all oscillator. Now let's go to waves. So I can essentially now say, well, what wave are we looking at now? Let's kind of piece it all together. What does the general wave look like? Y as a function of x and t is a sine of kx minus omega t. I've calculated everything there. So y as a function of x and t. What's the amplitude? I said 0.020. 0.020 meters times the sine. I'll go to brackets. K, wave number I calculated for you guys, I calculated 224.4. 224.4 radians per meter. X minus, so I'm still in here, minus omega t. Omega was 3.92 radians per second. I'm still on the board here. T. There you are. All right, so that's my wave. I mean, that is the wave based upon what I just got done doing. Now, one of the questions you're going to be asked is what's the maximum speed? So we'll just kind of keep this up here. So you're going to be asked the question, hang on one second. Page 6. Knowing the angular frequency and amplitude, what is the maximum speed of the surface of the water as it moves up and down? Okay, so that V max, again, what are you doing? This is how high above, this is your displacement of Y. This is a transverse wave. How do I know how fast it's going? Well, I would do a time rate of change of this, right? So I would say the velocity is given as the time rate of change of Y. Okay, and so again, if you don't understand this, that's okay. I'm taking a time rate of change, so a derivative of a sine is a cosine, and I would by a chain rule, I would pop out an extra factor of omega. So your velocity equation is actually going to be negative omega a sine of kx minus omega t. Well, you want V max. V max occurs at the maximum value of the sine, which is 1. So your V max, I mean, if I don't care about sine, S-I-G-N, is going to be omega A. Again, sine maxes out at 1. And so omega times A. So that's going to tell you what's the velocity, not propagation velocity. That's your phase velocity. Your phase velocity is your propagation velocity. This is the velocity of the water rising and falling. Okay, because this is your disturbance direction, Y. And so omega A. So omega again is 3.92 radians per second. A 0.020 meters. Your V max, again, this is the water height velocity, the velocity of how fast the water is rising and falling. It varies in time as well. The maximum velocity of that, or maximum speed. If I do this, let me calculate that real quick. 3.92 times 0.02, 0.078 meters per second, right? So that would be your answer, for instance, to, if I go to the page 6, just below the table on page 6 says, knowing the angular frequency and amplitude, what is the maximum speed of the surface of the water as it moves up and down? Well, there you go. It's going to be the maximum speed you can possibly see is 0.078 meters per second, or 7.8 centimeters per second. That's the maximum speed that you can experience. Two types of speeds going on here. Propagation velocity, that's your lambda times frequency. How high the water rises, the speed of the water rising and falling, that is what we just calculated here. Okay, two different velocities, so don't get them mixed up. All right, so we're done with page 5. I gave you you're going to says, write the equation. Well, that equation, you'll write this. That is the equation of your particular specific wave. I'm on page 6. Determine the frequency, wavelength, and phase velocity when you change the slider to min and then the max. Okay, and so in so doing, what you're going to do is you're going to, so this is a real quickie. Let me share screen again. Go back to, here it is. All right. All right, so I'm going to get the measuring stick out of here. We'll go back to the top view again. All right, so there we are. So what happens now if you select the frequency to min? So we're going to pick the minimum frequency possible. So we're going to slow it down, and I'm going to hit the refresh button real quick. So refresh. Okay, that makes everything go away, but I'll just do the following. I'll take my stopwatch back out. I'll make the frequency go to a minimum. I'll put the system in suspense, hit the pause button. Okay, and then I'm going to be everything ready. I'll hit the green button that allows me to start dropping the water. And I want to count how long it's going to take. And again, I want to also select the go button here. I'll figure how long 10 drops takes. Okay, so let's do that. Let's time out 10 drops. So let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. Hang on. All right. 37.95. Actually, yeah. So that's going to be, in fact, I was a little slow there. So why don't you, let's just use the data that I had. I had 37.6 when I did it. So write down 37.6. I was a little bit slow there. So 37.6 is what it really ought to be with the faster finger. So that's 37.6 seconds to do what? To time 10 of these drops. But you really want, so the T, I wrote T on the very top of the graph. You divide by 10, I got 3.76 when I did it. So that gives you the period, 3.76 seconds. Because it took 37.6 seconds for 10 of these drops to occur. And divide by 10, you get 3.76. So how do you get the frequency from that? 1 divided by 3.76. 1 divided by the period. So under min, the frequency should be 0.266 hertz. Now I'm going to try to get lambda. So I'm going to try to stop this thing right when a drop happens to get something that looks halfway decent. Let me wait one more time. All right, stop. Okay, so what I want to do is, let me let it go a little bit longer. There you go. All right. All I'm going to do is take my measuring tape and kind of go from some location, maybe the beginning of one of these circles, to maybe the beginning of the next circle. I mean, it's going to be a little bit rough. So we'll say 6.3 centimeters. So maybe 0.063. Again, it's not very pretty, but actually when I did it on my own, I did 0.066. Why don't we use that value? So my lambda, when I measured it, I got 6.6 centimeters when I did it by myself. So that would be 0.066 be the lambda value under min. You want to find the phase velocity? So again, my left column, my min column, my frequency is 0.266 hertz. My wavelength is 0.066 meters. I'm going to get the phase velocity. What I do, I multiply the two together because it's lambda f. So 0.266 times 0.066. I get 0.0176, I guess. So 0.0176 meters per second. That's the phase velocity with the minimum condition. What do you do for maximum? Well, hit the reset button. I'm going to maximize my frequency now. Be a faster experiment. I'll pull out my stopwatch. I'll put the system in suspense. So hit the pause button, hit the go button on the stopwatch, hit the green button on the water faucet. And ready to go. I'm going to count out 10 of these oscillations again. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Boom. Okay. So when you do that, I'll just give you the number that I got. I'm a little slow tonight, I guess. I did that. I got 10.30 as my answer. Here you see 10.44. I got 10.30. So so you divide that by 10, it's 1.03. So my period for the max was 1.03 seconds, so about 3 times faster. Frequency, again, 1 divided by the period. So the max column, the frequency column, I got 0.971 hertz. Lambda, well, let's stop this guy. What do we got? I'll try to stop it right at a drop. There we go. So it's a little easier to get lambda this time. So I'll pick the measuring tape, and I'll go from some location that I recognize, maybe beginning of a lip of a circle, to maybe another one, and I don't know, about 1 point. Whoops, that's not right. About 1.6 centimeters. So I'd write in the lambda row for the max column, I'd write 0.016 meters. You want to put an SI. You want to find the phase velocity, you multiply the frequency and the wavelength again. You multiply those two together, you get I get 0.0155 meters per second. Okay. Okay, we already answered the next thing. I'll let you do the practice. There's a table, you fill it out. Basically, on that table, you just pick off your graph. I'll do the first one for you, I guess. So y1, xt, you have a special graph. It's 10 sine 5x minus 3t. You read it. What is that again? It's y of x and t. It's a sine of kx minus omega t. Okay, what's omega? Read it off the graph, 3 radians per second. What's f? Well, f again is going to be, what's omega is 2 pi f. So f is going to be omega divided by 2 pi. You do that, omega divided, so 3 divided by 2 pi, you get 0.477 hertz. What's the period? The period is 1 divided by the frequency. So on that frequency cell, I got 0.477. I do 1 divided by 0.477, or 1 divided by f. I get a period of 2.096 seconds. K, well, what's K? Well, again, y is a times sine kx minus omega t. Well, K, you read it right off the graph, it's 5. 5 radians per meter. Lambda, how do you find lambda? Well, lambda is 2 pi divided by k. 2 pi divided by k. 2 pi divided by 5. My lambda, I get 1.26 meters. Next one over, A. That's the amplitude. Read that off the graph. That's 10 meters. Phase velocity. Again, phase velocity is a propagation velocity along the propagation direction, along the x direction. Lambda, f times lambda. F, 0.477 times lambda, 1.26. I get 0.601 meters per second. So I did the first row for you. I'll leave you to do the second and third rows. Okay, last part of this thing is kind of interesting. So you're going to set the frequency to be somewhere in the middle again. So again, we're almost done. So I'm going to hit the reset button. Put the frequency in the middle. So it's automatically in the middle. And set the frequency to be somewhere near the middle. Determine the value of the frequency and wavelength. Give the setting constant. Okay, so again, I'm just going to go with the previous values that I used. So I wrote in frequency. I put I got 0.629 hertz from previous data that I did. I got omega 3.95 radians per meter. Again, omega is 2 pi f. So I wrote a previous value down for the frequency, 0.629. Multiply by 2 pi. I get 3.95 because I'm going back to my original settings. That's why I know this. I just hit the reset button. Those are the default settings. So again, omegas, you get that. I get 3.95. That's because I calculated 2 pi times f. 2 pi times 0.629. My lambda, well, I got that from previous settings as well. I got that as 0.026 meters. My k, well, k is just what? 2 pi divided by lambda. So if I know lambda was measured previously to be 0.026, 2 pi divided by that, I got 241.7 radians per meter. Okay, so again, I'm just going off the default settings. So what we're going to do is we're going to do something a little bit different. We're going to grab this this little sensor, it's called a DWS. Oh, I forgot what that stands for again. That's yeah. Dual water level probe. All right, so dual water level sensor. Now what I'm going to do is I'm going to get this thing going, and then after I get it going for a while, I'll stop the simulation. So let's just let's just get it started. So let me start getting ready, hit the green button, and let's just kind of let this thing just have a fully developed waveform for the moment. All right, just kind of let it go for a little bit, and I'll stop it. All right, let me stop. I'm going to turn it on its side view. What I'm going to do is I'm going to stick a probe. So the first thing is put the sensors at the locations of the peaks. So I'm going to have 2 peaks. I want the ones that are developed, not the sloppy looking one, not the earlier one with the transients in it. I'm going to put it right at the location of developed peaks. There's 1 peak, and here is the other peak. And I'm just going to kind of sense the water level. All right, and I'm going to realize here I'm going to measure the distance between the 2 sensors. So let's measure that distance best I can. And I measure that distance. I get about 0.026 meters when I measure the distance between the 2 peaks. That's my wavelength, as you predicted, as I wrote above. Okay. And what I want to do now is I want to unpause simulation. I want to describe what the sensors are recording. So let's unpause it and let's continue. So look at that plot to the right. You notice that the sensors are recording the peaks at the same time and the troughs at the same time. They're in phase. So those 2 sensors are basically in phase when I have them set apart like this. Okay. And so what we can do, I'll just kind of I want to calculate K times delta X. All right. And so so you're going to do that here. That's number 4. So what's K? I'll just kind of read it to you here. You got K up there, 241.7 times delta X. That was 0.026. That's the distance between the 2 peaks. So 241.7, which is my value for K, which is a few lines up, times delta X, which is 0.026. I get that that's equal to 6.28. Then I want to do delta X divided by lambda. Delta X, 0.026 meters, divided by lambda, 0.026 meters. I find out that's equal to 1.00. So for number 4, my K delta X is 6.28. My delta X over lambda is 1.00. I'll pause the simulation. So let me try to get it at a good spot. All right. Oops, that's not a good spot. There you go. That's a good spot. Pause the simulation. And what I'm going to do now, I'm going to place one sensor at a peak and the other at a trough. So let me put this guy at a peak. I'm basically just changing the phases is what I'm doing. The other one I'm going to put at the corresponding trough. Okay. Again, it's just sensing the water height. And I'm going to get them going again, and let's look at what we see. And what you'll see, it's not very easy to see, but you notice that the 2 graphs are totally out of phase. So one is reading a peak at the same time the other one's reading a trough. They're 180 degrees out of phase. That's what you're seeing. You're essentially sampling the wave 180 degrees out of phase. What we can do is the same kind of thing again. We can do is we can measure delta X. Delta X is basically the distance from one sensor to the other. Ugh. Right. What the heck just happened? All right, I do not know. Anyway, when I measured, it was when I measured, it was 0.013 meters. All right, so I'm not going to play with that. All right, so when I measured, I got 0.013 meters. So my delta x was 0.013 meters. When I multiply k times delta x, I got k from above. K from above was, again, 241.7 times 0.013. I got 3.14. Delta x divided by lambda. Well, delta x is, now it's going to be 0.013. Lambda is 0.026. When you do the division, you get 0.50. So number 9, all it says is verify that for every omega over lambda equals n, for omega over lambda equals n, I'm sorry, back up. Number 9 says verify that every time delta x over lambda equals n, that the sensor outputs are synchronized. Yes, that would be the case. That was the first thing we did. You know, we basically had them in they're a wavelength, they're a single interval apart. You can do them 2 intervals apart if you wish. I just put a check mark next to that because I verified that. Verify that every time delta x over lambda is n plus 1/2. That's a half integral. Sensor outputs are completely out of phase. And we showed that as well. That's what we're showing right now. They're 180 degrees out of phase. Just a way of looking at phases. And that's it for this experiment. Any questions about that? Anything? I'm going to quickly kind of go through a little bit of review. Sorry it took so long, but you know, we're putting a size 10 foot and then size 8 shoes. So I'm on overtime right now. So I've been on overtime for most of the week actually. But any questions? All right, so let's talk about the review briefly. That's the example. So a little bit to this lab, and we kind of threw a lot together. I probably would have stopped at oscillations myself, but driving a wavelength anyway. But I didn't make the labs. So all right, so I'm done with the lab. Let's talk about the review. So let me kind of. Yes, sir.
Sorry, I just had a quick question. So since you're just going over the 5 today, is it okay if we ask you questions about the other 5 on Tuesday?
Well, you can. I mean, I'd rather have you guys kind of do those on your own. I mean, normally I'd go through the entire review, but you know, as you're taking a take-home test, I'm kind of going over the problems I find are the hardest.
Okay.
Otherwise, I'd be just giving the whole exam away for the most part. So that's the problem with this whole take-home. You know, everybody doing everything at home stuff. So I'm going to. So what I'm going to do right now is hoping you guys have the review questions in front of you. I'm just kind of, well, I guess I'll go back and forth here. So for problem 1, I kind of told you to go and look at OpenStack's example 6.4. I mean, problem 1 is essentially going to be a problem where you're talking about, you know, circular motion, you know, but you're talking about an object being on some circular platform that's being held on there by a coefficient of friction. So if you go back to my videos, OpenStack's example 6.4 does a pretty good job in showing you how to do that. So again, you're going to have a circular motion. There's going to be uniform circular motion. Again, this exam is over chapters 5, 6, 7, 8, 9. Chapter 5 is uniform circular motion. I mean, these problems occur in order. So the first problem will be a chapter 5 problem. So again, this is a uniform circular motion problem. So you'll be given a radius of your platform. You'll be given a period. You're gonna need the tangential speed. And then what you're going to do is you're going to set up Newton's second law in the radial direction. Again, the radial acceleration is the centripetal acceleration. And you'll equate that with the maximum force of static friction. You'll give me a frictional coefficient. I mean, very similar to what was going on in that example. Okay. So I'll leave that to you. So I think if we go back to the videos, you should see that. I want to do next, I want to talk about a more difficult problem. So let me share my screen real quick. Okay, I want to get rid of this. I'm going to kind of kill a few things I don't need anymore. Hang on one second. Otherwise, I have too much up. Oh, you know what? That's another thing I want to do too is I want to actually stop recording because I don't want to record my the exam part of this. So give me a second. I'm just saving stuff. Okay, pendulum. Computer is being challenged, its resources. All right, so let me kill Excel. All right, so I'm going to stop recording.